us to see the directions and the focus, in terms of research for our institute, for our department, and for our institute. So therefore, the current efforts of conducting this
It
particular
came now.
conference. Uh, yeah, yeah. Welcome, Dr. Baswaya.
Thank you very much. Finally,
Yeah,
I got it in.
yeah. Thank you. Thanks a lot. Yeah. So we have been able to start some research. My faculty colleagues are all are young and energetic, and they need obviously a certain kind of exposure in terms of various facets going on in chemical sciences to enrich and to strengthen their own programs, to focus the programs at IIT Tirupati. We already have a few projects and which are going on, and several PhD students. So we thought this is the right juncture wherein we could start meetings of this kind in order to bring exposure to the chemical sciences field to our own system, our own colleagues, our own students, as well others across the country, and maybe in future we'll extend it to even abroad as well. Okay, so in this effort, we have the invited lectures by eminent people, as you could see from the program. We have about 25 presentations, which I don't call it as a oral presentation. We called it as a flash presentation because we have planned these things in the form of posters, and posters is not a logical way of showing on screen. So therefore, we have converted these posters presentations into a flash presentations of running for about 4 minutes of each of these. I hope this gives a good platform for all the youngsters to sort of go through, get nurtured in the process of picking up the chemical sciences. The reason that I have taken this the recent trends in chemical sciences is because chemistry today has emerged as one of the largest area of science, and it is also coming out as a central science of all, having too many connections with interdisciplinarity. And this is the reason why we have taken at the present a general view. In future, we may have some micro symposia specializing individual ones. So with that view, we have tried to get the lectures in almost all areas of inorganic chemistry, organic chemistry, physical chemistry, theoretical chemistry, and as well materials and its kind of aspects that we have. I hope this provides a good platform for a lot of youngsters to learn, to get some ideas out of this, to forge in collaborations, etc. And with this, I welcome once again each and every one and to this particular symposium, and request everyone to make use of the opportunity that is given through this platform. Thank you very much.
Thank you, Professor C.P. Rao, for your welcome notes to all the participants, viewers, and attendees. We are thankful and privileged to have with us our friendly, energetic, and enthusiastic founding Honorable Director, Professor K.N. Satyanarayana. In spite of all these difficulties during this pandemic, his continuous support, encouragement, and wonderful leadership keeping us to move ahead. I will now request our Honorable Director, Professor K.N. Satyanarayana, to deliver his introductory remarks in this symposium.
Thank you, Gauri. Professor Rao, Professor Ganesh, number of our colleagues from various institutes in chemistry. Many of them have already interacted with us on many occasions. We had, when we started the IIT in 2015, the first, when we started putting together the curriculum for the undergraduate program, we had a lot of debate on how do we teach chemistry in the undergraduate program. And that's why Professor Rangarao at that time was part of our academic council, as we called it. And, IIT Madras was going towards one course in chemistry, but he and I were very clear that we should have at least two courses in chemistry. And we had structured it. And during the first 2 years, we had great support from people from faculty at IIT Madras, including Professor Rangarao, Professor Mangal Sundar, Professor Subramaniam, S. Subramaniam, Professor KK Bal Subramaniam, Professor MNS Rao. So they all had come, taught the courses here. They would travel here every week, teach the courses. And Professor MNS Rao, for example, came and set up our initial chemistry laboratory and structured how the experiment should be done and so on. So we had great support from them. And subsequently, I keep repeating this on many forums, the most difficult department I find hiring faculty is chemistry, from a good position to have, because you have a lot of applicants, too many applicants, and shortlisting process. So this requires a lot of help that IIT Madras had provided us, the group at IIT Madras, in terms of how we went around recruiting. So we took a decision that initially, when we started off our faculty hiring, given the number of applicants from chemistry, we'll start with theoretical chemistry, because that's a decision we had taken, because it was going to take us some time to set up our research laboratories, though we got our undergraduate laboratory ready. And we felt that if we bring in faculty members, we have to give them adequate support in terms of research facilities. That's why we started off in the first round by hiring about 3 faculty members in theoretical chemistry. Subsequently, one of the models that we have used at IIT Tirupati from the beginning is to bring in senior faculty members to guide in how we set up our overall institute programs, and specifically individual department programs. So we were very fortunate to have attracted faculty from IIT Madras, IIT Kanpur, IIT Bombay. Professor C.P. Rao came from IIT Bombay as senior colleagues who had just retired and came on re-employment. Government of India was supportive to understand that the new institutions need guidance, and they permitted us to do re-employment as a special case, because they were stopping the re-employment scheme. But specifically for the new IITs, they said, okay, we will permit this. So this helped us in bringing some very senior faculty members, and we could see, for example, in physics, recently we had launched this Center for Atomic, Molecular and Optical Sciences and Technologies in collaboration with IISER Tirupati, the guidance of people like Professor Deshmukh, who rallied the team around, and along with the IISER faculty, put together this center. So similarly, having people, eminent chemists like Professor C.P. Rao has, I'm sure, the chemistry department will grow very strongly. Another big advantage we have is our co-location with IISER Tirupati. So I always believe that when we talk about the faculty members, we should talk about the number of faculty members between IISER Tirupati and IIT Tirupati together, so that we share resources, whether it's from a faculty perspective or lab perspective and so on. And we are doing a lot of these things, activities together. And it's good that this program is being put together. We had the launch of our MSc program just a few weeks back. Again, we had some of you present at that time. Professor C.P. Rao had brought in quite a few chemistry luminaries to bless the program as it got started off. And so we need all the support in our initial years as we go forward, and look forward to very fruitful deliberations over today afternoon and tomorrow forenoon. And we were hoping to have you all come here in March, and the schedule was almost at the time when the lockdown was getting announced, and we took the call to postpone it. And I'm glad that we are able to do it now. So thank you everyone once again for coming forward in making this program a success. I'm glad to see that in this flash presentations, they got involved some of the colleges around Tirupati. So we need to create this ecosystem and linkages between the institutions around. Tirupati is turning out to be a major knowledge hub with a large number of institutions around, which again we should leverage. My only suggestion, if we are doing similar programs for Rao in future, is also, we've been talking about interdisciplinary. So it'll be good if we can bring in people who are working on the boundary of chemistry and say physics or biology, from those departments. You can say I have chemistry faculty working in related areas, or engineering, material science, and so on. I think that will slowly bring in the strong interdisciplinary initiatives between the chemistry department and the other departments and other institutions. So thank you very much, and all the best for this program. Thank you.
Thank you, Honorable Director, for your introductory remarks and suggestions. We will definitely consider next time. Thank you, sir, for your visionary talks. So now it is my again great honor and privilege to request Honorable Director of our neighboring institute, ISA Tirupati, Professor K. N. Ganesh, to deliver his opening remarks and formally launch our abstract book of this symposium. Although I do not need to give any introduction about Professor K. N. Ganesh in this August gathering, but for the students, I'll say a few words about him. Professor Ganesh was the founder and the 2 times director at ISER Pune before took the responsibility of the founding director of another institute, ISER Tirupati. He has received many awards and honors in his long, illustrious academic career. To say a few, Santisar Bhatnagar Prize. He is the fellow of all the academic, including fellow of Indian Academy of Sciences, Indian National Academy, Science Academy, and the World Academy of Sciences, JCO's Fellowship, and many more accolades. I will request Professor K. N. Ganesh, please share your experience and knowledge to the students in your opening remarks.
Yeah.
Okay. Thank you very much for your kind introduction. Let me also thank Professor C.P. Rao and Professor Satyanarayana for giving me this opportunity. And I think Professor C.P. Rao has already made an impact at Tirupati. This is the second gathering of chemists that he has organized within a short period of 1 month. I think all of us were missing opportunity to meet each other, and C.P. Rao has provided this unique opportunity twice recently for many of our chemistry colleagues to come and interact online. And also I was hoping that he would give me a chance to speak about my science, but he asked me to give opening remarks. I must tell you that when people ask you to chair a session or give opening remarks, there is a clear indication that we are not interested in hearing your science. You have done enough of your work. So you just advise us, you mentor us. So I thought I must take a little revenge on that. So I told him in the morning that I would like to just make a 10 to 15 minutes presentation on chemistry. Which is not my science. I'm not going to talk about my research. Since there are several young faculty here, and as C.P. Rao mentioned, chemistry has emerged as a central science. And Professor Satyanarayana also said that chemistry and biology and physics interface is very important. I think if chemistry has to keep its identity, it should not be chemistry, nothing but chemistry. Chemistry must expand into physics, biology, including mathematics, computer science, etc. That is the strength of chemistry. I don't know whether any other subjects have that strength. Chemistry can extend itself into material science, to earth and climate science. It's all nothing but chemistry. So I thought I should just give a different kind of about 15 minutes overview of chemistry, particularly for the young faculty. So if I can share my screen, I'll just show a small presentation on the importance of chemistry and the shape of things to come. I hope. Okay.
Should be able to share, yeah.
Yeah. Can you see that one? I see something desktop. Are you able to?
Yeah, it is coming now.
Yeah, it's coming. It's come.
It's coming.
Yeah.
Please go to the full screen mode, sir.
Okay. I'll go to
screen.
the screen mode.
Yeah.
See, what I wanted to talk to you, young people, is that if you are given a plenty of money and freedom, what would you like to do? Would you like to pursue research in area what is generally interesting, what is worth doing, or you would like to pick up area where you can only work? So there is a very, very important, distinction you have to make. As you grow up to future chemists, you must pick up problems which are worth solving, not just the problems that you can solve. So, quite some time back, I got interested in, if chemists are asked to name wishes, what is your wish? Then how would you go about it? So I asked my friends here, they would have all seen these papers, but for younger faculty, when you're choosing your new area, how do you go about it? Now, long time back, I'm sure all of you know about Richard Feynman. In 1958, I think he gave a talk in Caltech, and which is very well known as there is a plenty of room at the bottom. Science always proceeds. One is, of course, somebody determines, somebody asks tough questions, somebody asks impossible questions, and which will lead others to go through that. I'm not going to ask each of these questions. He simply said, why can't we write the entire 24 volumes of Encyclopedia Britannica on the head of a pin? This is a question he asked. And then he went on in that lecture in a short period of about 45 minutes. If you want to write, what are the things which are required? What kind of science is required? How do you write small? There is no point in writing small if you cannot read it. And how do you encode information? He said, we need to solve the problems of science. And he also said that, this is what he said. And he also said, only young students, young faculty can get into that. Now today, after about 60 years after that talk, I think today we have all these techniques, lithography to write small, you can use sensors, amplification, coding, encryption. So from the simple questions that he asked, all these techniques have come. This has led to the area of nanotechnology. And it is amazing how question asked about 60 years back has led to such fantastic developments. I'm not sure if I had not asked those questions, we would have been in the same position or not. So the important point is you must learn to ask questions, tough questions, impossible things sometimes, and that will certainly lead, if it is not for you, somebody else will try to take the lead. So this is a very, very classic, example of how tough questions were asked. Now, later on in 1990, a beautiful article written by George Whiteside, he asked a question, what will chemistry do in the next 20 years? He had 4 papers which I'm going to mention. I think I want all our young faculty to read it. This is 1990. George Whiteside, he asked this question, if chemistry has to be important, it has to survive, what are the various things? And I'm not going to show too much. What he said is that the pull of chemistry and the push, into basic research, they set the direction. In 1990, he said, if chemistry has to be relevant, it has to be directed towards addressing problems in these directions, like national security or, healthcare. These are the pulls. And the push is, if you want to develop then material chemistry, we have to develop polymers, surfaces, interfaces. For healthcare, biological chemistry. Within biological chemistry, chemists can provide, on molecular recognition, evolution, self-assembly. So he defined a whole charter of areas in 1990. And as you see today, it is still relevant. When people ask, what is the applications of chemistry you are doing, it is these areas that come into our mind: healthcare, environment, energy, and these things have become still relevant today. So 1990, he asked this question. In fact, he said that there are 4 scientific themes that will push chemistry: the chemistry of materials, polymers, man-made surfaces, interfaces, smart materials, manufacturing materials, environmentally compatible materials. And from the life sciences, we need to understand molecular recognition, evolution and self-assembly, bioenergetics. You see that in each of these areas, chemistry is the basic. It's very, very important. Then he said computation, the usual digital processors, they work on a binary concept of 0 and 1, whereas in many natural processors, a concept of neural network is used. It is the information is stored in connections of different strengths, not just in the binary mode, but strengths between different nodes. And these are all very hidden. So can chemistry provide an answer in analysis of, these kinds of connections? And then exploring the limits. George Whiteside said that we need to work on not just, our ordinary chemistry happening here, but we must be able to address very small systems, very fast systems, and very large systems. We require tools and techniques to, answer these things. For example, scanning, turning microscopy can go to very small dimensions and very fast. Nowadays we talk about not just femto, but even attosecond, 10 raised to the power of minus 18 seconds time scale. I think probably people say that if you go even faster than that, there won't be chemistry, there is only physics, they say that. So chemistry must address at the fastest processes that concern chemistry. And very large, when you say very large, how do you create very large electromagnetic field locally in a very, very tiny place, small places? And this can be done with lasers and lights. And if you do that, you can address at how to order particles, how to trap them, single atoms, light traps, materials with largest thermal conductivity. And so these are the areas which will lead you. So he very nicely said, chemistry must address at very small, very fast, and very large systems. And this is what is required. And it may not be very clear to you, but what it says is that, the various molecular processes which happen in different time scales are summarized here, 10 raised to the power of minus 15 and even 10 raised to the power of minus 18, people are now working on that. The thing is, how do you develop tools and techniques using physics to understand the properties of atoms and molecules at that time scale? And that was followed by somewhere in 1995, the previous was 1990. Accounts of chemical research carried a very nice issue saying holy grails of chemistry. In fact, it's a fantastic issue. As you know, grail actually means it is like a shallow dish with miraculous powers. If you have that dish, you can get, almost like Alauddin's lamp, you can achieve wonders. And what are those holy grails of chemistry was addressed in this Accounts of Chemical Research 1995 article, in which what was said was that, sorry, I have some problem in moving the slide. Okay. So in this holy grails of chemistry, what was identified was at that time, 1995, you must understand how to manipulate matter at the atomic level, how to develop room temperature semiconductors, quantum control, artificial photosynthesis, CH bond activation, how to create artificial enzymes, direct observation of the transition states in molecules, and how unnatural selections in chemical systems. As you see here, these are all new, maybe new terminologies for chemists at that time, but chemistry is at the heart of these things. And what was said in 1995, I think even today, it is still relevant. One can look back. Actually, if you see the latest Nature, there is an article on looking back, how much we have progressed under each of these directions, that is very important. So these are all the new ways of looking at science. I thought I must put up across to our young people, in choosing your problems, you must look at that. That was 1995. Now in 2017, Accounts of Chemical Research carried in another issue, Holy Grails in Chemistry, Part 2. Again, they talked about conversion and storage of solar energy, atomic scale manipulation, perfect catalysis, abundant clean water, air, understanding the origins of life, and wonder drugs, understanding the dark matter of DNA, that is the non-coding regions. And so all of these things, will have chemistry backup. Chemistry will play a central role in understanding many of these things. So as chemists, although we are trained in a conventional way, chemists have the ability to cross and go over and, take up problems from other. There are a lot of problems which are waiting to be solved with, for that chemists have to understand the language of physics, the language of biology. If you don't understand, it will be very, very difficult. So in 2017 was the state, Accounts of Chemical Research. Somewhere, I think I'm not going chronological order. In 2000, Stephen Lippert, I think we know Professor C.P. Rao, he worked with Stephen Lippert at MIT. He came with a beautiful article called Chemist's Wish List. That was the title of my presentation. In fact, it's a beautiful article which all of you must read, in this chemical engineering news, and which identifies the area, and about 20 different problems are suggested. Like, we want to create chemical entities comprising many identical components arranged in such a manner. This is a question. I think many of us young people, we have to start asking questions like this. If you want to solve a problem, what is the question you are asking? And then what is the science you can create? How to create, for example, self-replicating molecules and self-correcting chemical reactions. Understand the nature of a given desired new chemical transformation. There are plenty of them. I'm not going to do that. But this Revolution in Chemistry article by Stephen Lippert is a very revealing article. Now, in 2015, George Whitesides again wrote a beautiful article called Reinventing Chemistry. He asked a series of questions. If chemists have to remain in the central place, we need to ask questions like this. What is the molecular basis of life? How does the brain think? What is the microbiome? What is the climate instability? Everything you see, it is central part is the chemistry. Chemistry, the materials matter. So, by asking such questions, by putting that kind of demands, the science will progress. And computation at the simulation level, impossible materials, augmenting humans, many of these things can be solved not just with the chemistry, but with engineering, physics, in other areas taken together. He has put about 24 different items, a beautiful article, and each one of these things has written a paragraph of how chemists can play a role. And this is the only way. If chemistry has to remain relevant, we need to reach out. We had to, a lot of problems that are worth solving, chemists have to start thinking in a new way. Now, in 2015, Professor Govardhan Mehta, he and his colleague Stephen Maclean, they gave a beautiful commentary of role of chemistry in inventing a sustainable future. Now, why I'm mentioning is that each of these articles will give you, ways to think about that, how you can modulate your research to solve these problems. Many of them do require very basic understanding of, chemistry or making quantum, but the end result is in a societal product or a phenomena or a thing what is really important for the society. Again, this is a beautiful article about sustainable future, inventing chemistry. So let me conclude, for the youngsters, giving a message that the true value of a scientific quest comes from the journey. Of course, all these goals are important, but the journey is much more exciting. You may not reach where you want to go, but while attempting to go there, you discover a lot of new things. Himalayas can be climbed from different directions. Even if you don't reach the summit, Himalayas, but from different directions, you get a different view of the world. That is what most exciting thing about science. The second thing is the art of successful science often lies in being prepared to reorient your research goals. This is very, very important, particularly in the context of things what I mentioned, that we are good in something, but we need to reorient our capabilities to address new problems, and that's what leads to successful science. And finally, I can't leave without quoting from Mahatma Gandhi. We have celebrated the 150th year. He says that be the change what you want to see in others. It's easy for us to talk and sermon, particularly I would appeal to the middle-aged chemists to set up new trends, thinking of new ways so that our new youngsters, they start thinking in those directions. So when we are talking about recent trends, I think some of the things what I mentioned, I hope they're all, relevant to us. So with this thing, I would like to thank C.P. Rao for giving me this opportunity. And I'm sorry for exceeding my time limit, but I thought I must share these kinds of ideas with my young colleagues. And I wish the symposium a grand success. And as was mentioned by Professor Satyanarayana, the ISER Tirupati and IIT Tirupati, we are actually setting up new standards of, it's the only city where there is an IIT and ISER. So we would like to see that we set up a new model for, for the success of science. With these things, I thank you very much, and thank you for your kind attention.
Thank you. Yeah.
Thank you,
Gauri?
Professor.
Yeah.
Thank you, Professor K.N. Ganesh, for sharing your valuable thoughts and suggestions. And I'm sure it will be very, very useful for young faculty and also for us to choose the research projects judicially. Thank you, sir, for sharing this wonderful experience. So now I'll request Professor K.N. Ganesh to formally launch the abstract book of this symposium. Please give us a permission on behalf of you to
Yeah,
launch.
I'm very glad to release the abstract of the book. Thank you.
Thank you, Professor Ganesh, for launching the abstract book of the symposium. So before moving to the first session of this conference, I sincerely register my gratitude to thank our Honorable Director, Professor K.N. Satyanan, and Honorable Director of ISA Tirupati, Professor K.N. Ganesh, for giving their precious time and valuable suggestions to all the youngsters and all the students. I'd also like to thank our HOD, Professor C.P. Rao, for his presence and welcoming all the participants and viewers and attendees of this conference. So now we'll move to the next session, the technical session 1. So in this technical session, we have 5 distinguished speakers. All of them are very, very eminent in their own field. We'll start now. Yeah. So we have with us eminent distinguished scientist, Professor D. Basavaya from School of Chemistry, University of Hyderabad, in the synthetic organic chemistry domain. And then we have a second lecture from Professor G. Rangarao from the Department of Chemistry, IIT Madras. And then we have the third lecture from Professor K. Mangala Sundar from the same department, Department of Chemistry, IIT Madras. And then we have a fourth lecture with another distinguished professor, none other than my guru, Professor G. Mukesh from Department of Inorganic and Physical Chemistry, IISc Bangalore. And then the final concluding lecture of this particular technical sessions from the another eminent scientist from our neighboring institute, ISA Tirupati, from Professor Vijayamanan Mohanan Pillai. So before starting our this first sessions, I just briefly mention the rules of this session in 2 lines. I'm sure I no need to say anything to our distinguished speakers, as they all know the rules very well. So just to mention few words that each speaker will get a 20 minutes time, and I'll just ring a softly on bell 5 minutes before at 20 minutes, and then we'll have a extra 5 minutes for discussion and question answer. And I'll actually request all the participants and the students, if you have any questions, please post your questions at the chat box. So I'll moderate that. So if we can take all the questions in the 5 minutes, that is fine. If it is not, then I'll request you, please send your queries directly, email to the speakers. I'm sure they will be happy and glad to respond to your queries. So with that, we'll now start our first lecture that will be delivered by distinguished Professor D. Basavaya from the School of Chemistry, University of Hyderabad. So Professor D. Basavaya doesn't need any introduction to the scientific community, but for the students, I'll say few words about him. Professor Basavaya is the faculty of the School of Chemistry, University of Hyderabad since 1984, for almost 4 decades. When we talk about him, the first thing that comes to our mind is the Baylis-Hillman reaction, a novel carbon-carbon bond-forming reaction. His research is greatly influenced by this wonderful name reaction. He has given a new dimension of this atom economical carbon-carbon bond-forming reaction and gave high utility and wide popularity. His research paper on Baylis-Hillman reaction, published in Tetraheden in 90s, has received nearly 1,200 citations, and the chemical reviews on this particular reaction received nearly 2,000 citations. So he's a great teacher and received National Best Teacher Award in Chemistry 2008. He has published more than 100 research articles, many reviews, book chapters, with nearly overall 9,000 citations. He's a great teacher and inspiration to many students and teachers like us. So in his today's talk, he'll share his philosophy, vision, experience, and the recent contribution towards the continuous growth of this Baylis-Hillman reaction. So Professor Basavaya has received many awards and honors during his long illustrious career spanning over almost 4 decades. However, due to the time constraint, I will not be able to mention all his notable achievements. I register my humble apology in this regard. I request all the students to visit his homepage to get complete information about his research and accomplishment. Professor Basavaya obtained his MSc and PhD from Banaras Hindu University. He secured first rank and awarded gold medal in MSc Chemistry from BHU. He is a fellow of Indian Academy of Sciences, Bangalore, fellow of the Indian National Science Academy, and he was awarded J.C. Bose Fellowship, received BHU Distinguished Alumnus Award in 2012, and Honorary Professor, Department of Chemistry, BHU, and many more accolades. I shall stop here and request Professor Basavaya to deliver his lecture on Bayes-Hillman reaction. Please, sir.
Thank you very much for your nice words of introduction. First of all, I would like to thank Dr. Pullarao for inviting me to this wonderful symposium. Let me share my screen. Not able to share screen.
No, sir, down you can see one green arrow which is showing share screen. If you click that, couple of short thumbnail of different windows which are open on your computer it will show. And you please select that particular window where your talk is being highlighted.
I opened that window.
Share screen, and you have to select those from the small windows your talk. No, if we just share the screen, then we'll find. After sharing, can you please open your PPT?
I opened already. We opened, but not coming on the thing.
Sir, we can share your PPT if you want.
No, I think it's difficult for me. I should only handle it. No?
Yes, sir. Sir, did you do the share screen?
I did share screening. Let me do again, otherwise. You are only coming. Mine is not coming. Your screen only coming to share the screen.
So then you please share entire desktop. If you click whatever option is coming, you please share.
Yeah, please keep the PowerPoint file open and then share. You need to keep that file open. The other file.
Open that point. Open that one.
Okay.
Shall I try and see whether it is working?
Sure, sir.
I will try this one. Let's see whether it will work or not.
Well, it's working because Professor Ganesh could share his screen.
Yeah, correct. Are you seeing my?
Yours I'm seeing. Yours I'm seeing.
Okay, so that means it is working, and Professor Ganesh also presented his this one. So
that's a nice try, Rangarav. You are showing them their own program.
How to do this problem?
Maybe we can flip the talks while we figure out this thing. The next speaker could start, and in the meantime, figure out how to get his thing up.
Yeah, that might be a good idea. You flip the talk so that somebody can actually help him from remote over the mobile.
Okay, you can talk. Other talk you can talk. I will talk afterwards.
That will conserve the time, but it won't change the order.
Yeah,
Fine.
we can start off with Rangarao.
Yes, fine, no problem.
Maybe we can send this PPT file by email to organizers.
I sent yesterday.
They have it, but he wants to only control it.
Okay.
Not able to do it actually. I don't know.
So, shall we, sir, move the next speaker?
Yeah.
You can have the next speaker.
Sorry, sir. Yeah, so we'll look into the next after this talk. So now,
Very briefly, please, very briefly, don't take too much time.
yes, sir. Yes, sir. Thank you, sir. So now we'll have the next distinguished speaker, Professor G. Rangarao, and he's from the faculty at the Department of Chemistry, Indian Institute of Technology, Madras, and his main research interest on the surface chemistry, heterogeneous catalysts, developing new materials for energy storage, electrocatalysis, photo and thermocatalytic hydrogen production. He has his research article, ultra-layered copper oxide structure with high porosity of high performance supercapacitor applications in the Journal of Physical Chemistry C has resulted in nearly 800 citations in few years. This is amazing. He has published more than 150 research articles, many reviews, and book chapters. He was a visiting faculty of many foreign universities, including Institute of Molecular Science, Japan, University of Augsburg, Germany, and many. He also received many fellowships. To name a few: DAT Fellowship, Germany, STA Fellowship, Japan, and Japan Industrial Technology Association Fellowship, and many more. He's a great teacher and inspiration to many students and teachers like us.
ACK, I'm not open to by sharing not coming. Can you help me? Yes, can you?
So I'll request all the students to visit his homepage to get complete information about him and his research accomplishment. In today's talk, he'll describe the hydrogen production using indigenous Syria-based materials by thermocatalytic method. I invite Professor Rangarao to deliver his lecture.
Okay, can you see my slide now?
Yes, sir.
Okay, so let's begin. Okay, so thank you very much, Dr. Rai, for that introduction. I am very happy that to participate in this first virtual symposium conducted by IIT Tirupati. I'm sure we will have many more in future. I'm also quite happy to meet all my colleagues, all my friends from other institutes, IAAC and every, the IITs, Vijay Mohan and IISER. So I would also like to say that Professor Ganesh has given a fantastic 15 minutes introduction, how science should be done. And in that, he one of the holy grails in chemistry, which has been mentioned for many times, was solar energy, and then was conversion and storage. And then Professor Satyanarayana, Professor Ganesh also mentioned there should be interdisciplinary departmental work should be done, and then where chemistry can actually get connected to other subjects, engineering subjects. So my talk is going to be precisely that, covering all these aspects. So I'm going to talk about particularly the title is basically the hydrogen production. That's what I'm interested in. That too using indigenous materials, using a thermocatalytic reactor built in IIT Madras. That is a task that I have taken up some time ago. So basically, these are the quick outline of what I'm going to talk about. Renewable energy, hydrogen is a carrier basically. Why do we need hydrogen? I'll come in subsequent slides. And hydrogen economy, particularly in Indian context, and then how do we produce hydrogen? And there are several approaches which I will talk about. And then redox chemistry, particularly rare earth oxides like Syria and cerium dioxide and other materials can be very good materials for this kind of hydrogen production. And then some structural aspects of these materials, and then the reactor which we have built, and then the preliminary experiment that we have done to show that hydrogen production is possible. Of course, we have done it in the reactor, in the home built reactor in the lab. So the point I'm saying is here that we have to worry about two molecules in future. In future means the next 30 to 40 to 50 years. We have to worry about this. Number one, H2O. Number two, CO2. Water and carbon dioxide. I'll tell you the reasons why you had to worry about these two molecules. For example, in global emissions, CO2 is a big problem now. CO2 emission globally. In 2019, 43 billion tons of CO2 has been added to atmosphere, which is actually leading to what is called global warming and then all those climatic difficulties that we have. And so currently atmospheric CO2 levels are sitting around 410 to 415 ppm. 60 years ago, the same CO2 levels were less than 300 ppm. Now, suppose say if you reach, we have reached 300 to 415 very fast in 60 years. So from 300, 415 to 450 if you reach, and that is going to be a potentially disastrous climatic condition that we're going to face. So important thing is we have to somehow reduce the CO2 emissions, not only the natural way, but I think we have to cut down CO2 production or CO2, how to convert CO2, recycle CO2 is another question what the scientists can think about. Decarbonization and then limit the increase of global average temperature, because this CO2, the moment you pump into the atmosphere, it is going to increase the temperature. The average temperature is 13.9 degrees, and the increase should not be more than 1.5 degrees centigrade. If it is beyond that, I think we will be touching very temperatures which we will not be able to, which will not be bearable. So alternately, what has been suggested is the hydrogen economy concept. So when you talk about hydrogen economy, you have to have low environmental impact. So we need to see how to produce hydrogen as a carrier, and then how to currently this hydrogen is produced using fossil fuels, nuclear, renewable energy sources, and so on and so forth. The amount of hydrogen generated currently is the order of 10 to the power of 10 kilograms per year. So, and this is not sufficient. This is going to go increase when you talk about hydrogen economy. So, but how do we produce this hydrogen without carbon, without producing carbon dioxide or in carbonaceous materials? So there are a lot of technological issues here.
Mute and unmute. Unmute is there. No, what are you doing there?
There are a lot of technological barriers here, particularly applications are also plenty are there. I think a lot of background noise is there.
Achha.
So now if you see here, these are some of the references which I am talking about here. For example, in 1970, John Bockris has already talked about, predicted 50 years back, predicted solar hydrogen alternative as an alternative energy. That was the first prediction that he made. Immediately after that, Fukushima Honda generated, did an experiment and published in 1972 on hydrogen generation. And then there are a number of papers came out slowly. And then recently also there are papers which I'm seeing. This is Professor Sina Rao's paper. He is doing a lot of work on that. And there is another paper here which is a kind of a review. Now, why we need hydrogen? Solar hydrogen is going to be a future energy carrier, and we have to get ready for hydrogen as an energy, and it should be a hydrogen economy in India. I think it's going to be another 20 years from now. Already Japan is doing it, and we have not even looked at it till now. This is something which is, I think, government of India must be thinking about. Now, the hydrogen production is very important because it is clean, it is renewable, it is sustainable energy carrier. So we should be able to make use of this resource, because the hydrogen basically comes from water. So you have plenty of hydrogen there, plenty of water, plenty of hydrogen. And currently world's supply is 15 trillion moles of hydrogen per year. And then by 2050, the hydrogen required is 645 billion normal meter cube. That much of hydrogen is required. So So basically, when the issues are, we produce hydrogen, we need to store it. That storage is a big problem because it's a gas phase, it's a gas at room temperature, even low temperatures also. So we need to compress it, and people have been working on metal hydrates to store hydrogen. And you can convert hydrogen to methanol, hydrocarbons, and then use them as fuel, liquid fuels, so on and so forth. And then once you have all these, you need to look at the domestic distribution, transportation, etc. And if it has to be something like like what we have the petrol stations, you have to have awareness, infrastructure, etc. have to be worked out. And of course, there are plenty of applications for hydrogen. So it can produce electricity, for example, fuel cell. Professor Vijay Mohan is there, and hydrogen fuel vehicles can be will come already in other places, other countries. People are trying these hydrogen fuel vehicles, and then you can have burn it and get heat, power generation, and you can also convert it, use it for methanol, ethanol, and kind of chemicals you can produce, ammonia, synthesis gas, which is also very important for chemical for synthesizing simple chemicals, and you can actually store it as a clean energy also. But currently the problem is H2 cannot compete with the normal fuels which are available in the market. So, but as the time passes, and this is going to be a very important resource, energy resource, particularly for our country. So there are several methods already existing in the literature, in the industry, water electrolysis using solar photovoltaic. This is a fairly established one, but it involves a lot of expenditure. And biomass processing, fermentation route to produce hydrogen, photobiological, thermal, wind, coal, oil, hydrogen power, hydropower for hydrogen generation large scale. These are all now people are working in different areas. Some of them are commercially already established processes. The other one is photoelectrochemical method, where one can use sunlight and electricity. And the last two blue ones which you are seeing here, the visible light induced photokinetic water splitting. This is a semiconductor-based process where TiO2 is a what you call material which nobody can beat it till now, but people are trying to change, find new materials, TiO2 based or radiated materials. One of them is GC3 and 4 carbon-based material, carbon nitride, which we have published in this particular journal recently. The one I am going to talk about is this one, the last one, thermal decomposition of water using thermochemical redox cycles. Normally, these thermochemical redox cycles are operated at very high temperatures, something like 2000 degrees centigrade. And then at that temperature, you can dissociate steam. So you need to have proper materials and reactors, etc., to tackle this high temperature process. So these are some of the production methods, and then their efficiencies are given here in this table: steam reforming, partial oxidation, autothermal reforming, biogas gasification, electrolysis. All these are all commercial already, really commercial. The last two are just being explored, and I'm sure in Japan I was told that photocatalysis method, they have actually developed what do you call that, a frame where they coat this and then expose it to sunlight, and then they start getting hydrogen bubbles. And we need to do that in India immediately because we have a lot of sunlight, and then we should be able to do that. So this is long term, but long term means I guess in another 10 years, I'm sure these things will come out as important ways of generating hydrogen. So I'm going to look at. So actually, I'm now looking at these two areas in my lab here, apart from many other things which I do. So if you see here in nature has a nice way of converting CO2 to wood and all that. It's very efficient. Similarly, if you see, so this is you get CO2 and then get the organic compounds like wood and all that. You can burn it again, go to CO2. There's a nice cycle established already here. That means the CO2 can go to chemicals or some wood or chemicals. You burn it, you get CO2 energy, and CO2 again, can be fixed by, for example, vegetation. But the point here is, this is a cyclic process. The only thing is we are pumping too much of CO2 that the vegetation is not sufficient to convert CO2 to wood. Can we have similar cycle like where H2O can be split in, hydrogen can be produced from H2O, burn it and get H2O and energy, and then this H2O can also be can it be recycled? That is the question that we need to ask. This is basically I am posing this this question based on what nature is doing. So that's where I am saying the CO2 H2O molecules are going to be very important for future. So this is what is going to happen. It's a recycling of water and hydrogen. Can it be? Is it possible? It should be possible. We should make it possible. So H2O goes to H2 and oxygen, and then this right now electricity, people are using electricity, but can you use sunlight to do this? And then you need to have some huge amount of delta G, that is plus 237 kilojoules per mole, which is huge. If you convert that into electron volts, it's going to be 2.46 electron volts per molecule. So somewhere in 1998, in Journal of Catalysis, it's reported that that cerium oxide can be packed in a reactor and pass CH4, and you get hydrogen and CO. Similarly, CO2 and H2O can be sent here, and then you get CO and H2. So this was one of the thought-provoking paper where the cerium dioxide has been is proposed to be a material which can actually generate CO and hydrogen. So based on that, people have been working on across the world in Europe and other places. What they have done, what people are doing is that you have a redox cycle where you have these metal oxides are mainly the ones which are being explored. Of course, there are other ways of people are doing it, but this is a high temperature process. So where you have this metal oxide here, and this metal oxide, if you heat it 1000 degrees centigrade, it loses oxygen. So you get metal oxide, reduced metal oxide. That means a lot of defects will be there, anionic defects, oxygen defects will be there, and then it gives out oxygen. And this again, if you take it along this cycle and then expose it to CO2 or H2O, it will grab this oxygen, leaving the CO and H2. Since this gas, or it can be hydrogen, or it can be CO itself. So this happens at high temperatures, 1000 degrees centigrade. We want to do it at 1000 degrees centigrade. Normally, it is more than 1500 degrees centigrade. That's the main hurdle. At that temperature, how do we manage the process? So then and then it goes back, and then you expose it to. You can regenerate it by once this oxygen is grabbed here. This will get oxidized, and then it will go to oxidized state, and then it will go on and on. So it's a cyclic process. So through this process, one can generate a lot of things from syngas, for example, and then they can be used in all other, producing petrochemicals, alcohols, fuels, electricity generation, so on and so forth. So this is a very important game which people are playing, and which is not an easy thing. But in Switzerland, I know there is an institute which actually built a reactor, and they are testing various materials. They even wanted me also to send my materials there for testing, because we don't have this reactor in India till now. So the metal oxides, people are working on these are the metal oxides, but there are the limitations. Zinc oxide, it will just evaporate. So that is the problem here. Perovskites are being explored now. This AB, one of them can be rare earth metal, and so on and so forth. I'm now going to focus on cerium dioxide, which I've been working on since 1997, 96. So I'm going to look at that one. So generally what happens is, when you have these oxide systems, particularly example CO2, as I mentioned in the cycle, the MO at high temperature gets reduced. So you have a oxygen defects here, oxygen is released, and then this oxygen, if this oxide is exposed to water or CO2 are together, you can get oxidized metal oxide back, and then it will give you hydrogen and CO. Suppose if similarly, this is the oxidation reaction, and this is going to be the reduction reaction. So these two, if you combine, you get net reaction where you get H2 and CO2, H2 and CO2 giving rise to H2 and CO and oxygen. This is a net reaction. So let me just the key aspect in this cerium dioxide is basically the CO2 goes to C2O3. So 3 plus here and 4 plus here. It switches between 3 plus and 4 plus and back to 4 plus. So at different temperatures. That is a very important and interesting property in this material. So quickly to look at the cerium dioxide, it has a cubic structure. All these blue ones are oxygens, and then the yellow ones are ceria. What is important, interesting thing in this is that you can actually pull out this oxygen without disturbing the cubic structure. So it acts like a sponge. That's the beauty of this. You know, you will not have to remove that. So it has tetrahedra. This is a tetrahedra. These are all oxygen. This is oxygen, and these are this is ceria, and then in the center you have oxygen. So this OC for tetrahedra you have, and then you have CO8 cube. Suppose if you take this as a cube, it looks like a cube here. You can see here. So these are oxygens, and then you have the cerium at the center. So what you are going to do is you are going to remove these oxygens without disturbing the fluoride structure. So one of the important things is the non-stoichiometry of this cerium dioxide is a very important property which will help us to split water. And in the process, it retains its fluoride structure, and then it can breathe in and breathe out oxygen. These are the important things. Of course, it has some changes in the crystal structure. If you pure cerium dioxide, if you take these are the ranges of temperatures where this one is stable up to 900 degrees centigrade, and then between these two temperatures, the cubic Ce2O3 can be stable, and so on and so forth. But we're not worry much about it. What is more important here is that the CO2 forms some beautiful solid solution when you dope zirconium 4+ ions in that, because the radius is slightly different. The cerium 4+ zirconium 4+, there's a slight difference in the radius. Okay, so let me go quickly. So if I substitute zirconium, I can say the zirconium substitution can be seen in the XRD. You can see this major peak is shifting here. That is an indication that zirconium is substituted. So important thing is that we need to have high surface area to remove oxygen. You need to have doping. You can also have metal particles with ceria. So these are the things which will help us to split to use it as a material for thermogravity reactor. Okay, let me just quickly. I think time is running out. So this is basically the reduction profiles of cerium dioxide powders. And for example, the powder which has surface area 1.5 meters square per gram, and this is a powder 30 meters square per gram. This is a powder with surface area 130 meters square per gram. You see how there is a strong dependence of reduction properties, reduction of ceria on the surface area. You can see that the surface area is very low, and as you increase the surface area, you start seeing there is a strong reduction peak developing at very low temperatures, almost like 600, 700 Kelvin. Whereas high surface area material is only reducing at about 1000 degrees centigrade. So this is one of the things which you need to keep in mind. So surface area is very important for low temperature oxygen exchange. Now, suppose if you take those same materials, same cerium dioxide, and add small amount of rhodium, this is basically catalysis kind of work. If you put rhodium on that, this peak which we are seeing, low temperature reduction peak, is now reducing, is coming back even much lower at much lower temperatures, something like 350 to 450 degrees Kelvin. Almost room temperature is reducing. That means you are able to exchange oxygen even at low temperatures. So that is an important property that we need to see. So the oxidation reduction should be possible at very low temperatures in this material. Now the point is, but it will get sintered. You start with high surface material, it gets sintered. So what we need to do is to offset that, you substitute zirconium into that, so that the sintering process is arrested to some extent. So in this case, what happens is we have substituted zirconium here. This is pure cerium. There are two peaks here which I have showed you earlier. The moment you substitute zirconium, the two peaks merge and then give you a single reduction peak around 800 degrees Kelvin. That's good. That is one of the interesting things. So this will also have high oxygen exchange property, which is called oxygen storage capacity. The higher the oxygen storage capacity, the better the material for the production of hydrogen. And then, of course, we have added some rhodium in this, and then you see that the entire reduction is now shifted to very low temperatures here. So one important point I want to show you is that I wanted to compare these 4 different materials. CuO2, very low temperature, 1 meter square per gram sample. This is also 1 meter square per gram. These are all very low surface area. Suppose say we can't start with high surface area materials because at 1000 degrees centigrade, the surface area will disappear. So if you start low surface area material and still look at the reduction properties, you can see here this particular material in the presence of metal particles, it is reducing beautifully. Even the surface area is very low, 1 meter square per gram. See, it is reducing, huge reduction process is there. That is happening around 700 Kelvin. So that is very interesting actually. So that means if you have this kind of a material, you will be able to use it for this purpose. Okay. Now, having said that, let's come to cerium dioxide again. If you take 1 mole of cerium dioxide, you can actually get half mole of hydrogen. That is 65 ml of hydrogen per gram of pure CO2. In terms of millimoles, 2.9 millimoles. But practically, this is just not possible. If you get about 5 ml of hydrogen per gram of cerium oxide, that is really good enough. Because it needs temperature more than 2000 degrees centigrade. So as a result, as I mentioned to you earlier, we can dope zirconium and many other metal ions to find out which is the more suitable. But zirconium is the one which we can actually look at. So we have done this, gadolinium, iron, zirconium, so on and so forth in different compositions. We have done it. And what we found is this particular material is giving us 4.3 ml per gram of hydrogen. This is estimated from TGA analysis in the lab. So even pure cerium dioxide is also not giving that much. So it is better to have a doped system, either zirconia, maybe some other metal element also can be doped. So based on this, we estimated, suppose if you take 4 ml per cycle, if you use this material and then try to do that cycle, low temperature, high temperature cycle, which may take about 10 minutes, let us say, if you build a reactor, which is very good reactor, if in 4 ml, you can produce in one cycle in 10 minutes. And then in 300 minutes per day operation, 300 minutes means I'm just saying about 5 hours. So you get 120 ml of hydrogen per gram of per gram of the ceria zirconia. Now in 5 hours operation, 4 ml per cycle per 100 grams, if you could try this per gram, you get 12 liters of hydrogen, which is about half a mole. That is really very good, very good, very good, what I would say, yield of hydrogen using this material. Now the point is that this material, if you use commercial cerium dioxide, is very expensive. So what we did, we turned to Indian Rare Earths Limited, which produces a lot of, they produce all these thorium and all these reactor materials. Cerium dioxide is one of the side product, which is actually they say that a lot of it is there. They don't know what to do with that. So we said, give that material to us, and we will try it out. So we made cost benefit analysis here, and we found that cerium dioxide is very is very cheap. For example, in this case, yield is very high, the cost is very low. So our own material, indigenous materials, can be used. It need not be, one of the important things is it need not be pure cerium dioxide. It can be there can be impurities. In fact, if you have impurities, it is even better. So our own material, which is available within India, can be used for this purpose. That is the point I'm trying to bring out here. So using this material, we have made variety of samples, powders, pellets, foams, and extrudates of various things. So some of them are not very stable, but we have tried making all these kind of things and tested these materials, and we built a reactor design. This is where I wanted to tell Professor Satyanarayana has mentioned, he wants to have cross-discipline research. This is where I have taken help from metallurgy department and also mechanical engineering department and students, gun chemistry, all three of us came together and we built this reactor. This is the reactor here. You can see this is a GC to analyze hydrogen. This is the reactor here, and you have a condenser and then hydrogen collecting mechanism behind. This took a lot of time. This is about we spent quite a bit of money on this. About I don't remember, maybe 20-30 lakhs on that. There's a student who did this good job, and then using this reactor, we have tested those materials. What we did is we tried to reduce those materials which we have made, Syria zirconia materials, using nitrogen gas, simple nitrogen gas. So we have pellet, which is reduced in nitrogen, and then we have foam, which was reduced in nitrogen again, and we have again pellet reduced in hydrogen. What is interesting here is the nitrogen reduced sample, either foam or pellet, they are producing much better amount of hydrogen here. So the reduction is done at 1050 degrees centigrade, and the oxidation is done at 900 degrees centigrade. This is high temperature. This is a cycle basically. So you subject your sample to 150 degrees centigrade, bring it back to 900, again take it to 150, again bring it back to 900. But that is a very important achievement. We have not been able to make that kind of a reactor which can do fast cycling in India. It requires several crores of investment and a commitment by researchers and also funding agencies. I'm sure this is the first step. I have made this. This has been doing for me for the last 10 years. I have made this first step, and I'm going to use this reactor, whatever that lab scale reactor, to do these more and more of these experiments. We have also tried, for example, here Syria zirconia here, Syria first cycle. See, you can see Syria first cycle, it produces a lot of hydrogen, but second cycle it is gone. It gets sintered. But then when the Syria zirconia, it is the first cycle, and then second cycle and third cycle. See, second cycle it may have come down, but third cycle, it has gone up. So this is a fairly stable way of doing it. You can use this particular process. That's what is hinted here. Also, you can see hydrogen generated. This is the first cycle. Huge amount of hydrogen is generated per gram of catalyst, and then but the second cycle it has come down. Second cycle is this red one. So whereas Syria zirconia, we still have a good amount of hydrogen, between 0 to 150 minutes. This is actually, we have collected it for several hours to ensure that, all the hydrogen is collected, which is coming out of the system. We also have tested this material, whether this material is stable or not. The phases are stable. So this is the, after second cycle, we have this, and third cycle, we have this. So this is basically fairly stable. This is a cubic system actually. So there is some other phases have formed here, but essentially the major phase remains same. Your second cycle also at 1100 degrees centigrade, and then 900 degrees centigrade. So this is the experiment. Again, we have done it on this year. We have compared, the initial samples should be reduced in nitrogen or inert atmosphere or hydrogen is the question. We was thinking that hydrogen would do a better job, but to our surprise, nitrogen in the flow of nitrogen, if you heat the sample to 1000 degrees centigrade, 1050 degrees centigrade, it is getting reduced. That is a very interesting thing. We don't need to worry about hydrogen. So you can see here the nitrogen reducer sample produces a good amount of volume of hydrogen in this particular system. Okay, so let me conclude. I don't know how much time I have taken. Let me conclude saying that the hydrogen production has been demonstrated in the lab scale thermochemical reactor. That is one of the things I am very happy to say that. But that is only a first step. There are several steps we have to move forward. And people in Europe and other places, they are building huge reactors. For example, Germany, the DLR laboratory is there. They are doing fantastically. They're building solar reactors to test various materials to produce hydrogen. And then other thing is the defect chemistry is important. If you make more and more defects, the material is going to be more and more active for water splitting. And then doping is very important, as I showed you doping. If you have doping not only in water, you can also split CO2 to CO. So that is also possible. So that way you can also help yourself. We can help ourselves converting CO2 to CO. one of the important things is that we should be able to do this process at less than 1000 degrees centigrade. We have shown at 1050 degrees centigrade. I think it is possible to do this reaction between 800 to 1000 degrees centigrade. We don't need to go to very high temperature like 1500 degrees centigrade. So if that is the case, a solar reactor can be built which can be operated at 1000 degrees centigrade, where various materials can be tested, indigenous materials for the production of hydrogen. This can be an industry of its own. I'm very sure when a couple of decades, maybe 20, 30 years later, this is going to come up in a big way in everywhere in the world. And then, so the critical thing here is building a solar reactor which can actually do this work. This is something which we have to take up in a serious manner in our country. And then, so designing new materials with high oxygen storage capacity using indigenous rare earths are very important. That is another thing where R&D is required. Research and development is required to produce new materials for this purpose. So let me just, that is a reactor and thermokinetic reactor, where we demonstrated hydrogen production is possible. This is funded by MHRD and Thermax in Pune. And then these are the people, and actually I would give 80% credit to this girl. She's the one who built this reactor patiently, spending nearly about 8 months to 1 year. She's a mechanical engineering student, but guided by me. So that is very interesting. And in fact, now she learned so much of chemistry from me. Whereas this boy is a postdoc, and he actually is the one who made all these materials. He and there are a couple of others who designed, who made these various materials. And then now we are now slowly testing those materials in this reactor. So this is Dr. Mukhtar. This is now she just now got her degree, finished her Viva was. So she is Somasri. She is now in IISc Bangalore. She is doing postdoc there, but still she is still writing manuscripts with me, sitting in IISc. Professor Mukesh, and also collaborators. Dr. R.R. Sonde, he's a industrialist. Nagesh Kenny from Thermax. These people have analyzed our samples using their facilities. They have good facilities there. So we have to take all these people into consideration. And this is Professor Sundar Rajan from Mechanical Engineering Department of our IIT Madras, Ravi Kumar from IIT Metallurgy Department. So we as a team worked on this. But the thing is, there's a lot more to achieve in this area. That's what I would say. With that, I think I would like to thank Professor Pollarao and also IIT Tirupati for giving me this opportunity to present this piece of work which we have done. So thank you all.
Thank you, Professor Rangarao, for your wonderful talk on oxidation reduction on the surface of ceria oxide and the doped ceria oxides. So due to time constraint, I'll just take one question that we have in the chat. So,
Dr. Roy, I think we better avoid questions because there's not much time. There's a lot already. We are going late.
yeah. So yeah, I'll just send.
Let them so they can always send the questions so we can forward it.
Yes, sir. Yes, sir.
Are there any questions at all?
Yeah, sir. In the chat, 2 questions are there. You can always look into it. So maybe we can
look into and respond. Rangaro.
Okay.
Yeah.
Okay.
Thank you once again, sir. Thank you so much
for
the wonderful talk. So can you please, sir? Yeah. Thank you. Now I'll invite Professor Basavaya. Sir, please share your slides.
Is it ready? Is it ready? Is Professor Basavaya, are you ready? He has to remove the unmute.
Yes, yes. So we managed to send some students from Professor Nangia's lab.
Okay.
So he has guided. I think Basavaya sir will be ready.
Up to unmute.
Yeah.
Can you unmute?
Please unmute. Please unmute.
He has to unmute. He has kept his yeah. Yes. Fine. Sir, now you
side.
Yeah, your screen is coming. So you please share the PPT. Yes.
Excellent, sir. We can see it.
We can see.
You can see slides?
Yes, sir. So you can make it. Yeah.
Now,
Okay, thank you.
Full screen.
Full screen.
Okay, thank you very much.
Yeah,
Please,
Excellent.
I'm sorry for that problem in handling the slides. So
Not
first
at
of all, I
all.
would like to thank Dr. Pollarao and his team for inviting me to this wonderful symposium. Let me, before I start my lecture, I would like to see what is actually the philosophy of my research. Before I go to philosophy of research, I would like to tell briefly about philosophy of thinking. The way we think is very important in life. Okay? The way we think will lead to success or failure in our life. For example, I give two examples here. One example is here. You have taken number 9. Number 9 can be viewed as 3 into 3 or 10 minus 1 or 18 by 2. There are so many ways of viewing number 9. Therefore, object is one. Perceptions are so many. Object is one. Perceptions are so many. Okay. Other example. Let me give other example. This object is here. If ask any mathematics student, he will say it is a rhombus. Ask any chemistry person, he will say cyclobutane. If you ask a non-chemistry person, non-mathematics person, he thinks a diamond ornament. Or who play cards, in playing cards, he thinks it's a diamond in playing cards. You can see this one. This is the example. Therefore, this is the object. This is the way a mathematics person can think. This is the way a chemist student can think, like cyclobutane. A common man is a 4-line boundary. Those who play cards, they think it's a diamond in playing cards. Therefore, what is not there is important. What we think is important. Let me go to our research of philosophy of our research. Okay. Functional groups are very important things in organic chemistry. They play a very important role in organic synthesis. Okay. I'll give you, there are some important functional groups which are written here. Carbonyl, maybe keto, aldehyde, ester, or acid, or amide. Hydroxy, amino, nitrile, alkene, I selected 6 functional groups. Okay. Let me tell you briefly. I selected 3 groups here: carbonyl, hydroxy, and alkene. The properties of one functional group. I give you 3 examples here. One is keto, other one is alkene and hydroxy group. The keto group is here. You can convert it into hydroxy group by using appropriate reduction, or you can do insert oxygen by using any oxidizing reaction like Bezier oxidation, or you can do a nucleophilic reaction, you get tertiary alcohol, or if you have CH2 here, you can generate a carbon and do chemistry. Therefore, carbonyl group can itself do so many properties. You can convert tertiary alcohol, you can get secondary alcohol, you can convert into ester, you can convert it into homologated molecule. Suppose you take other molecule like alkene, you can convert it into diol by appropriate reagent, or you can cleave homolytically to give 2 carbonyl compounds. You can reduce the appropriate reagent to get corresponding hydrocarbon, or you can insert carbon or oxygen, cyclopropane. Therefore, alkene has so many properties. Okay, I given 4 important properties here. Next, I'll go to hydroxy group. All of you know these things. Reminder: you can oxidize to keto group, you can convert into halo group, you can convert it into olefin by appropriate dehydrating agent, or you can dehydroxylate to get the corresponding alkane. Therefore, these all give one functional group properties. There are 2 functional groups together in a molecule. How they look at it? The 2 groups are there. Far away, they have their own properties. 2 functional groups. If they are nearby, okay, like this, I have selected 2 groups here, hydroxy and alkene. They are quite far away by 6-7 carbon apart. They have their own properties. If they are nearby, you can see this forms a very good substrate for Johnson-Claisen rearrangement or Claisen rearrangement to get the corresponding alkene esters. Or you can generate carbocation and do so much chemistry here. Therefore, 2 functional groups are there nearby. In addition to their own properties, you can get extra bonus properties like Claisen rearrangement or like this carbocation generation very fast. Other example I have taken here is alkene and ketone. They are far away. They have their own properties. They are nearby, okay, like this. Okay, they are nearby. You can do Michael reaction here to get corresponding alkylated compound, or it can actually do Diels-Alder reaction here using it as a dienophile and diene to get the corresponding pyrene molecule. Therefore, The two functional groups are there nearby. Okay, in addition to their own properties, you can get a lot of extra properties, bonus points. See, now, our idea is there are three functional groups are there in a molecule. They are far away anyway, they have their own properties. They are close by. They have, in addition to their own properties, they can give a lot of interesting applications and properties. So look at the molecules like this. You can see I selected three functional groups here: hydroxy, alkene, and ketone. Okay. Imaginarily, theoretically, you can have in a cyclic system only four types of molecules. Okay. Okay. Hydroxy, alkene, ketone. Hydroxy, alkene, ketone. You can see this is alkene in the middle, alkene in the middle. Olefin has two, therefore they can have two different ways, and also ketone in the middle, or hydroxy in the middle. There are only four ways a cyclic system. You can have molecules like this, three functional groups in a proximity. Go to cyclic systems, okay, all the three in one ring. Okay, all the three: hydroxy, ketone, and olefin. Hydroxy, ketone, olefin, all in one ring. All in one ring. Here, olefin in the middle, CO in the middle, hydroxy in the middle. Okay, because of the ring size and heteroatoms, you can have so many varieties of molecules. They are all the three in one ring. Other one is two in the ring, one out of the ring. You can see olefin here, hydra of the ring, now olefin in the middle, okay, olefin in the middle like this. Therefore, there are so many ways of making this. Okay, there are so many ways. Okay, because of heteroatoms, ring size, you can have number of molecules having two functions in the ring, one out of the ring. Okay, you can here OH out of the ring, olefin out of the ring, yeah, here ketone out of the ring. Therefore, there are so many ways of making cyclic molecules, two functional groups in cyclic system. Other example we have is, okay, one in the ring, two out of the ring. One in the ring, two out of the ring. Therefore, you can see here, olefin in the ring, hydroxy in the ring, ketone in the ring. There are so many ways of making functional groups. Therefore, if you want to construct molecules having three functional groups, close proximity, there are thousands of ways of constructing these molecules. All these molecules, not many of them are known. How to make them? Our philosophy is how to make them. Our whole work is we predict that the molecules containing three functional groups in proximity, will, in addition to their own properties, they provide new directions and concepts in organic chemistry. This is our main vision. Therefore, what we can do is we can develop methods of making molecules having three functional groups in proximity, okay, and investigate their properties and application. These are the actual main aim of our research. How to develop strategies, methodologies to make molecules having three functional groups in close proximity and study their properties, okay, in organic synthesis. Because all molecules you can't make. In the pursuit of this philosophy, we developed a reaction called Bellis-Hillman reaction, which produces three functional groups. You can see alkene, electron withdrawing group, can be keto group, aldehyde group, nitrile group, or amine group, hydroxy group, or amino group. Because developed a reaction from a known patent by Bellis-Hillman, by these two gentlemen, Bellis and Hillman. This reaction provides three functional groups, alpha alpha to each other. A very simple reaction. It is actually, you can also call it as CH functional reaction. Okay. This we call it as activated alkene. This we call electrophile, the catalyst. Okay. This H is functionalized to give the corresponding amino or hydroxy molecule here. Okay. This reaction we have been working for the last 36 years in Hyderabad University and made significant contributions. This talk will describe only recent contributions of work in this direction. Let me tell before the reaction mechanism. Reaction mechanism is believed to have the first addition of catalyst on activated alkene to generate deuterionic enolate. The deuterionic enolate reacts with aldehyde in aldol fashion, generate the CC bond, then it releases the catalyst to produce the multifunctional molecule. Okay. This is the MEK there. It also undergoes some side product. It reacts with itself to give the minor product. This one. The overall reaction is produces two molecules, okay? One major, one minor. It happens only in the case of methyl valent ketone. If you take methyl acrylate, acrylate, they are not as reactive as methyl valent ketone. Therefore, you get only this compound is not obtained. Only this is obtained. Now, this talk will present only our recent work. Let me give this thing. This is a isoquinolinium salt. Isoquinolinium salt. This is a very good electrophile. You can add any nucleophile here. This is already known literature. This was used as our electrophile in Bellis-Hillman reaction. How it can be produced? You can produce this one very easily by taking alkynyl benzaldehydes in the presence of amine to get the corresponding imine, which are in reaction with silver triplet. Okay, we get the isoquinolinium salt, which reacts with any activated alkene, Bellis-Hillman manner, use the corresponding base product. This is the actually new electrophile. We have used it. This known molecule we have used efficiently to generate the Bellis-Hillman compound. This is the reaction mechanism. Okay, how it goes exactly. We also proved the mechanism on the all intermediates which are using HRMS studies. Anybody want, they can go and look for this in this published paper. They are the intermediate. This is the mass spectrum. We have proved these things. This is the mass HRMS studies. These intermediates are actually proved by exact mass spectrometry. And next, I will go to less reactive components in Bellis-Hillman reaction. A Bellis-Hillman reaction, I tell you, activated alkenes, alkyl valent ketones, acrylates, they are very reactive species. Therefore, they are well known in Bellis-Hillman reaction. Electrophiles also, ketoesters, aldehydes are very well known electrophiles. Whereas acrylamides, vinyl sulfoxides, vinyl sulfones are very less reactive. They are not that used in Bellis-Hillman reaction. Whereas electrophetone, allyl halides, epoxy also, they are not that much electrophilic in nature. Therefore, they are also not used that effectively in Bellis-Hillman reaction. Our main purpose is to use these less privileged electrophiles in Bellis-Hillman reaction. Okay. Because intermolecular reactions are much faster than intermolecular reactions. We first wanted to do this substrate in intermolecular reaction. Intermolecular reaction means activated alkene and electrophile. To do reaction here, you get a cycle. Okay. If a substrate contains both activated alkene and electrophile, then you can do Bellis-Hillman reaction here to get the corresponding cyclic molecule. These are Bellis-Hillman reactions. I told you wanted to use less reactive acrylamides as in the reaction aldehyde. Normally, this substrate alone will not react with aldehyde that easily. Okay? You need a lot of special conditions. We thought that if they are in cyclic system, that they can undergo, because intramolecular reactions are much faster in entropy wise, enthalpy wise. Therefore, you can do the Bellis-Hillman reaction here. Therefore, we have prepared representative substrates like using classical chemistry. This is a substrate. You can do Bellis-Hillman reaction by using appropriate catalyst, Japco. Japanese reaction here, you get the corresponding adduct. Similarly, you also get the 5-member ring. That means acrylamides, they react very fast. Okay? Reaction times are not in a normal reaction. It takes few days. Here it was hours only. Therefore, acrylamides, you can use it intramolecular reaction as a fast reactive substrate. We are also done with spiro compounds making appropriate substrate for Bellis-Hillman reaction. This amide reacts with ketone. We have also used. We also showed the asymmetric reaction by using whatever available in our lab. We need get the. That means if you use a better catalyst here, instead of better catalyst, we can get the better selectivity. You want to show the idea works. Therefore, anybody wants to, you can use better catalyst and do. Now, ketones. I told you ketones are also less reactive in Bellis-Hillman reaction. Here, less reactive person, less reactive person. Two less reactive persons, you made it effective in Bellis-Hillman reaction. You made the substrates using classical chemistry, then you can see this reacts here to give the corresponding adduct. Therefore, react with ketone, which never reacts in Bellis-Hillman reaction otherwise. Also, acrylamide, which are less reactive in Bellis-Hillman reaction, they are together in the cyclic system, intramolecular fashion. They work nicely in reasonably shorter times. We have also done diastereoselective selective reactions here. If you have already a chiral center in racemic form, is a racemic compound, then you can do Bellis-Hillman reaction here. It gives you actually syn selectivity, high syn selectivity reaction. You have also done is 5-member rings. You get this in measure. You get. Next, I will go to two-component Bellis-Hillman reaction. Two-component Bellis-Hillman reaction. What is two-component Bellis-Hillman reaction? It can be done three ways: a substrate containing activated alkene, electrophile component, and catalyst, or you can do substrate containing activated alkene, a promoter, and electrophile reacting with, or a substrate containing electrophile and a promoter, and reacting with activated alkene. There are three ways of doing. I am going to describe only one way. Here I am going to describe a substrate containing electrophile plus promoter and reacting with activated alkene. Let me tell you, this is the substrate. Substrate containing, this is the promoter site. Hello? This is electrophilic site. Therefore, this is the two components are. Two components are there here. It can react. It can react here and it can react. I give you how it works. It activate alkene. It react like this. It goes like this. This is a component Bellis-Hillman reaction. This is the way the mechanism works. Reacts in aldol fashion to generate the corresponding aldol product, which gives Schindler-Lewin derivative. The reaction works very well with variety of activated generate the corresponding Bellis-Hillman product. It's a simple reaction. You take iridium carboxyl head, which has promoter site. This is also electrophilic site. It reacts with activated alkenes to give the corresponding Schindler-Lewin derivative. It also works with 6-member rings, cyclic rings, to give the tricyclic compound. It also gives tricyclic compound. Means this works well with any activated alkene, a cyclic or cyclic, to produce the corresponding Bellis-Hillman products. How ketones also work in the reaction here. Ketone also, I told you, less electrophilic in nature. They also work very nicely here. To prepare this kind of molecules, simple classical chemistry. R is methyl or phenyl butyl ring. This gives you, this is Bellis-Hillman product, because this position is very reactive species, very reactive. It also further undergoes Bigel reaction to give further reaction product. Therefore, Bellis-Hillman reaction works well with less reactive ketones also. The cyclic compound is there. This get nicely tricyclic compounds. It also works with this kind of pyridine ketones. Methyl valine ketone generate tricyclic molecule. You get it is a cyclohexenone. You get tetracyclic molecule in one part operation. Let me tell you briefly applications of Bellis-Hillman products, because I think I have some time. How to look at the Bellis-Hillman product? There are three functional groups. You tune them properly. Appropriately, you can use them as a substrate for very, very different type of organic transferase methodologies. How do you look at the molecule? See, this is the molecule. This is the molecule you have. You can look at 6 different ways. This is where allylic alcohol you can think. This is unsaturated ester ketone. This is actually, you can think as beta hydroxy ester or ketone, like this. Only alkene, only ester or ketone, or only alcohol. Therefore, there are 6 different ways of looking at the molecule. Therefore, accordingly, you can plan your synthetic schemes. Allylic alcohol or ester or hydroxy ester or alkene. Therefore, 6 different ways of reactions you can do. I give some examples. Also, some other important things are there. You can generate Bellis-Hillman alcohol to acetate or bromide, which can be converted into sulfonium salts by using dialkyl sulfides can convert into ammonium salts by using trialkylamine, or you can convert phosphonium salts using trialkylphosphine. Therefore, they are very reactive intermediates. These substrates can be transformed into phosphonium salt, ammonium salt, or sulfonium salt. They are very, very reactive substrate in organic chemistry. Also, you can use them as SN2 reactions or SN2 primary reaction. You can add here or you can add here. Like therefore, it is a great source of reactive intermediates. I use some examples of these reactions. Okay, the simple reaction: you take allyl bromide, you add sulfide, you get sulfonium salts. This is a very good 1,3 dipole. I give some examples here. Okay, this is the penicillin bromide. You can get a dipole. It reacts with dead diazo dicarboxylates to generate the corresponding pyrrolizole system. Therefore, penicillin bromides acts as a very good 1,3 dipoles for reacting within any dipole profiles in a 3+2 cyclic manner to generate the pyrrolizole derivative. So done. So many examples like this. Other example I will give is I give you these 3 bromides. We have selected here 3 bromides. This is no stereochemistry. Here cis stereochemistry. These 2 are cis. These 2 are trans. These 2 are trans. These 2 are cis here. Therefore, it has no stereochemistry. How it reacts with substrates? You have done with substrate as isotin derivative. It gives you pyrazole compound. It gives you pyrazole compound. But whereas this bromide gives you epoxide. Okay. This bromide gives you this kind of styro compound, exclusive stereoactivity like this. Therefore, there are 3 reactivities. No stereochemistry get styro compound. Okay. If you have hindered ester, you get the epoxide. If you have this kind of compound where aryl and nitrile are cis together, you get again spiro compound with exclusive stereochemistry, these 2 on the same site. Therefore, the stereochemistry will decide the way of reactivity. Also, the steric factors also will decide the way of reactivity. I'm coming to the end of my last thing. These are very important molecules. Spirolactone and spiro, these oxidol molecules. These are the recent molecules. Some time back they told they are very important reactivity. How to make them using Belisian chemistry? This is the Belisian acetate. You have taken oxindole. You can alkylate it here. Then you can get corresponding cinnamic acid type molecule. Then you can do a cyclase here. How to do this thing? I'll show you quickly. You can alkylate using Belisian acetate. First, you get a carbanion, use sodium hydride. You can add this one, you get the corresponding cinematic ester. You can add this FIFA, trifluoroacetate phenolidide, you can get the corresponding lactone. This is the reaction mechanism as given here. This is the FIFA. Then reaction forms like this. Then you get this oxygen will react here to neutralize the nitrogen salt. Then you get the corresponding. I think I am going to finish it now. Thus, you can easily make these kind of spiroxindoles and lactones using Belsinodextrin. Before I close my lecture, I would like to thank my students who have done a lot of work all these years. I only have 3, 4, all page students have left my group. Only now presently these 3 students are there working. Also, I would like to thank DST, CISR, Hyderabad University, and I'll finally thank you very much.
Thank you, sir, for a wonderful talk on Bayes-Hillman reactions. So, any questions? No questions. Okay, due to the time constraints, so we'll move to the next speaker. So next speaker is our eminent speaker is Professor Mangala Sundara Krishnan. He is also faculty from same department, IIT Madras, as our previous speaker, Professor Rangarao. So he is currently a professor and head of the chemistry department at IIT Madras. His main research interest is on the theoretical chemistry and quantum information processing. and theoretical molecular and magnetic resonance spectroscopy. So apart from the wonderful research he is carrying out at IIT Madras, his contribution on technology enhanced learning program in modern India is commendable. He is one of the founder coordinator of National Web Course Coordinator NPTEL project and also chief coordinator of DTH Sam Prabha. So with this brief introduction, I'll kindly request Professor Mangalasundar Krishnan to deliver his lecture on revisiting the microwave spectra of benzene water and the other van der Waals complexes with benzene like hexafluorobenzene water complexes through Coriolis interactions. Professor Mangalasundar, please, sir.
Yeah, please unmute. Unmute.
Yeah, good afternoon. Can you hear me now?
Yes.
Okay, thank you. So let me first of all thank all of you for the invitation as well as for your kind introduction. So I actually went to the website to list down all the colleagues whom I already know. That is yourself, Professor Pullar Rao, Professor Arun Manna, Dr. Debashish, Dr. Gandhiban, and Dr. Rajiv. This was for working together to bring this symposium to a very, very fruitful process and purpose for all the students. So this is my sincere thanks. Let me just quickly go to the talk, since you said it's 25 minutes and then 20 minutes, and probably towards the end it should shrink down even further. Let me quickly go to the presentation, which is, it's a theoretical presentation. You can give me any amount of time, still you will feel uncomfortable that you haven't understood parts of it because I haven't explained it well. But in any case, we will try our best, okay? So I hope you are able to see my screen now.
Yes, yes.
Yeah, revisiting the microwave spectra of benzene water and other van der Waals complexes, other complexes with benzene through Coriolis interactions. The phenomenon of Coriolis interactions is not a very commonly understood phenomenon in chemistry students among the spectroscopy teaching. Many of us do understand centrifugal forces in microwave spectroscopy, rotational spectroscopy. Very rarely we come across Coriolis, but I must tell you that I spent a lot more time on understanding the Coriolis interactions from the molecular Hamiltonian for more than a decade or so. So let me give you a little bit of my introduction. The person with whom I started this whole project many years ago as a postdoc was Dr. Carrington, who was then in the University of Montreal, but now in Queen's University. He's a chair professor there. And my long-term collaborator and currently very active collaborator, not only guiding me, but also pushing me to clarify many things is Professor Arunan, also a very personal friend of mine for the last 20 years. And all the others are my students who have contributed to my understanding, Dr. Karthikeyan, Dr. Ramprasad Bora, and currently the PhD student who has submitted the thesis is Mr. Prasanth Halda. This talk is from his thesis. Okay. Let me explain what Coriolis and centrifugal forces are. If that at the end of this talk is clear to you, then I have achieved purpose one. The purpose two is then to look at what the Hamiltonian does. The Coriolis and centrifugal forces are essentially due to descriptions based on a non-inertial coordinate system. The best example that we can think of is our own Earth, which is rotating, and we are gravitationally bound to the Earth. Therefore, our coordinate system, in a sense, is fixed to the center of the Earth. And the fictitious forces that we feel, which are not described by the Galilean frame, the standard Newtonian frame, the fictitious forces are Coriolis and centrifugal forces. Now, they depend on the aspects of the rotation of the object. In the case of molecules, the molecules rotates, the molecules vibrate. Therefore, there is the rotating, vibrating molecule. The motion is coupled to each other, each degrees of freedom. And if the molecule rotates with an angular velocity omega, and if the atoms in the molecule vibrate with a vibrational velocity v about the center of mass, while their position is r, the Coriolis term comes from the classical expression of r dot v cross omega. This is a cross product of the vibrational velocity or vibrational momentum. mv is vibrational momentum, and the r omega will eventually lead to an angular momentum, rotational angular momentum. So it is a linear coupling between the vibrational angular momentum and this is the vibrational angular momentum component, and this is the rotational angular component. You need a vibrational velocity for the Coriolis energy to be present and Coriolis interactions to be present. On the other hand, even if the molecules don't vibrate, which is an approximation of 0-point energy with an average equilibrium configuration, and we do not worry about the molecular vibration in, say, when we say rigid rotor Hamiltonian. The rigid rotor Hamiltonian is m omega square r square, and the mr square is the moment of inertia. And therefore, you can see that the omega square introduces what is called the centrifugal energy term, because the r will be a function of the point masses where they are and so on. Therefore, this centrifugal energy does not require a vibrational velocity, but it is resident there. As long as the molecule is rotating, the atoms will feel a centrifugal force about themselves. But if in addition they also vibrate, they will feel this Coriolis energy. The Coriolis energy is linear in angular momentum. The centrifugal energy is bilinear or quadratic in angular momentum. Where do you see these? Gaspard Gustave de Coriolis is the first one to visualize these things in the early days of classical mechanics, when every French physicist and German physicists and mathematicians were looking at the Newtonian mechanics and all the other basic descriptions of physics. And he came up with this beautiful article called Sur les équations de mouvement relative de système de corps. And he came up with the equations of motion of a rotating system and relative to the static frame. That's what it means. And he also introduced in thermodynamics later the term work and kinetic energy in mechanics as well as in engineering mathematics. So he's credited with that. It is in his honor, this term. And none of you can forget this image when you see it, the cyclonic image. All the time, the cyclone on the northern hemisphere rotates in a certain direction, and in the southern hemisphere, it rotates in the opposite direction. These are exact or verbatim implications of the Coriolis energy. Because the air currents continuously move, they have an angular velocity, and they have a sort of a mass associated with them, as well as they are rotating along with the Earth, and therefore you see that the motion of the clouds between different points on the Earth is not a direct line, but it is a circular line. The circular force is essentially what we call as the Coriolis force. And the other example that you are all familiar with the Coriolis force is the tidal force that is also due to the Coriolis effects, because the Earth is rotating at the same time that the ocean, the water mass is also moving around. Okay. Now, in molecular system, how do we see the Coriolis force? So here is a very simple example, very beautifully illustrated by Herbert Jahn, one of the founder, the physicist who is credited with the Jahn-Teller effect. Herbert Jahn in 1939 gave a very beautiful picture of the Coriolis coupling. And here is a triatomic molecule, ozone, which has one normal mode of vibration in this direction, and another normal mode, which is the symmetric vibrational mode, symmetric stretch. And then this is the asymmetric stretch, and then you have the bending mode. The bending mode, essentially, that the atoms bend towards with the bending angle being slightly larger. But this is a slightly, what do you call, a motion with a lesser amplitude, a larger amplitude, but with a smaller frequency. Now, this molecule definitely vibrates about the respective positions with the center mass somewhere here, but it also rotates. Let us consider a rotation in the plane, which means that the angular momentum is perpendicular to the plane towards you, coming from the screen. Now, if you imagine that the angular momentum is coming towards you, and if this is the linear velocity of the atom, the cross product of this and the angular momentum at this point perpendicular to you will give you a motion which is effectively in this direction, because the cross product is perpendicular to both the vectors. Therefore, this vector as well as the perpendicular vector, the cross product is the vector that is in this direction. And that's what you see in this normal mode. And likewise for this atom, the R cross V dot omega or R dot V cross omega, it doesn't matter. This force with the rotational motion will give you a force in this direction, and likewise this will give you in this direction. Therefore, if this normal vibration is acted on by a very strong rotational motion, this normal mode tends to experience a force that is like this normal mode. Therefore, these two normal vibrational frequencies can couple with each other because of the rotation, and therefore you have an angular momentum coupling with the vibrational angular momentum and a rotational angular momentum. This is the origin of the Coriolis force. It's a V cross omega which is responsible. This was recognized as early as 1936, and later when the molecular Hamiltonian was written in its beautiful form, the current form that we use today, due to James K.G. Watson in 1968, he came up with the exact expression for the rotational vibrational kinetic energy of the molecule that includes all these terms except the V. And all these terms are essentially J square mu. Mu is inverse moment of inertia. Therefore, this is J square by I equivalent to the rotational kinetic energy. And pi is the vibrational angular momentum. Therefore, you can see pi inverse moment J is the Coriolis term. And then the pi is the vibrational angular momentum that contributes to the vibrational energy. Doesn't depend on rotational coordinates. Then you have the harmonic oscillator momenta and the harmonic oscillator coordinates coming from the potential energy. Therefore, you have in this Hamiltonian all the terms that you need to know. And the pi is the vibrational angular momentum that is coupling the vibrational P, the momenta, to the vibrational coordinate Q. Therefore, this is the Coriolis force when it is coupled with the angular momentum J. And these are called the Coriolis coupling constants. Thousands and thousands of molecules. The microwave spectra have been examined very carefully using the Watson-Hamiltonian and using the Watson-Hamiltonian with many different expansions. There is this famous expansion of the Watson-Hamiltonian using vibrational terms only, and the Coriolis terms only, and the rotational terms. The rotational terms will all contain the centrifugal energy term, and this will all contain 1, 1, 1, 1. This means one rotational operator, and 2, 3, 4 represent the vibrational operators. Therefore, the unharmonic corrections are here, 3, 0, 4, 0. These are all unharmonic Hamiltonian. This is the harmonic vibrational Hamiltonian. This is the rigid rotor rotational Hamiltonian. You can see that this expansion is an exact expansion. And as a result of this, finally, one comes up with the use of what we call as the reduced rotational Hamiltonian for each and every vibrational state of the molecule. This is a very elaborate procedure. Of course, one has to go through the literature and probably go through several years of understanding the contact transformation and details. But then in the end, microwave spectroscopy gets a benefit of being able to have a molecular Hamiltonian for each vibrational state of the molecule, each vibration state as identified using the normal modes. The first 3 terms represent your familiar rigid rotor terms. The next 3 terms that you see, as well as these 2, they are all 4th order in angular momenta. So these are called the centrifugal effects, J4, J square, JZ square, JZ4, and then this is an anti-commutator, therefore it is a J square, J plus square, J square, J minus square, JZ square, J plus square, JZ square, J minus square. All these terms, these are centrifugal corrections. There is no Coriolis term in this. This is still centrifugal correction. And this is the higher order centrifugal correction. All these things are exactly derived in the spectroscopy. And Watson's effort is phenomenal in coming through the final expressions. These are what used in fitting the molecular spectra. They use only centrifugal distortions. And Coriolis term being a linear term in rotational angular momentum, it cannot be reduced to 0. Descartes originally suggested that it can only be minimized, which is mathematically correct. And therefore, high resolution molecular spectra for semi-rigid molecules often contain both the Coriolis and centrifugal terms, in addition to other anharmonic resonance terms such as Fermi and Darling-Denison resonance terms. All these are put together, and one diagonalizes a polyad or multiple vibrational states whose frequencies are very close to each other, and then obtains the entire energy structure and fit to the molecular Hamiltonian. Okay, so this is the process. And this process, of course, I learned all of it as a postdoctoral fellow in the lab of Tucker Carrington for many years. And then 2 of my students, Karthikeyan and currently now present yet are the people who are looking at this in more detail. Now, exactly what is the problem with the van der Waals complex? How does it manifest itself in the complexes, rigid, semi-rigid versus non-rigid molecular complexes? The Hamiltonian that I mentioned in just a few minutes ago as an effective rotational Hamiltonian is for a semi-rigid molecule. For a rigid molecule, of course, there is no vibration. The moments of inertia don't change. That's an idealized model. Molecules are not rigid. Even at 0 Kelvin, they vibrate with a 0-point energy. Therefore, we have semi-rigid molecules, but now van der Waals complexes are all non-rigid molecules. How are rotation, vibration, and torsional motion if a fragment of a molecule rotates relatively freely with respect to the other? Then we call it as torsion. How are these things manifest in van der Waals complexes? Now, most of the practical high-resolution spectra of van der Waals complexes that I understood for quite some time contain basically a ground state rotational constants fitting a geometry, which is a reasonably good geometry, verified experimentally through the spectroscopic constants. And a large majority of them turn out to be symmetric tops at the ground state. When the torsional motion is a free rotation, we will see what that means. Let me see if I have a picture here. Give you an example of the benzene water. Then we'll come back. Yeah, this is an example. Okay, the benzene water complex is such that the benzene is the base and the water molecule is right above the pi cloud with one hydrogen pointing towards it. It's not exactly symmetric as you see it. It's the one hydrogen pointing towards it, but the axis of rotation of the water molecule goes through the C6 axis. Now, this distance is close to 3 angstroms. Therefore, this is a weak force. Now, this water molecule, if it is stationary, this is an asymmetric top by design, by the structure. But the water molecule rotates freely, relatively freely, because the potential energy for the rotational motion is, the potential barrier is very, very small. And the free rotation essentially means the water molecule is seen as one spherical blob, and benzene with a sphere on top of the C6 axis is still a symmetric top. Therefore, we see the symmetric top's ground state spectrum. Now let me go back to that. So the ground state rotational constants and the fact that they turn out to be symmetric tops and the fact that there is a torsional motion being a free rotation has enabled the people to fit the molecule using the coupling between torsion and rotation instead of coupling between rotation and vibration. The fundamental change that Prasenjit introduced over 30 years of thinking is to replace the coupling between torsional motion and free rotation, which many people have been using for all these years to fit many van der Waals complex spectra and not able to fit all of them, by coupling between free rotation and vibrational motion of a symmetric top. Therefore, symmetric top has degenerate vibrational bending modes. And these bending modes of very low frequency can couple with free rotation. Therefore, he replaced the whole thinking of torsional vibration, rotational coupling to vibration rotation coupling. Therefore, even when you have excited torsional state quantum numbers, the ground vibrational state is still mentioned all the time in the previous fits, whereas in our fit, we changed the whole thing. So what does that mean, all of it? What it means is that Coriolis coupling does not contribute to the ground vibrational state energy. It's the matrix elements for the ground vibrational state for the Coriolis terms are all exactly 0. Therefore, the rotational transitions for the ground vibrational state will not see any Coriolis coupling at all. You have to excite the molecular state, vibrational state to the first excited vibration states. And if there are two normal modes which are very similar in frequencies, like I said in the very beginning, then you will be able to see the Coriolis coupling. But in all the spectra so far, that has not been interpreted that way. All vibrational modes with 0 quantum number, basic state, ground state, and centrifugal coupling contributes because it's independent of the vibrational velocity. And therefore, what people tried to do was to use centrifugal coupling and expansion. And as a result, the formal theory for the asymmetric tops that was given by Watson and others was extended to include a torsional barrier, but including the Coriolis coupling in a slightly different way. Let me give you the torsional Hamiltonian. A typical torsional Hamiltonian is very elaborate, but let me just give you this. The first three terms are the rotational Hamiltonian. The P's are all the angular momenta, and P gamma is the torsional angular momentum. Therefore, you see rotation, torsion, coupling. This 1 minus cos 2 gamma comes from the torsional potential energy, therefore it's a coordinate. Therefore, you can see that this is the potential energy due to torsion. And then again, you can see the rotational angular momentum here, P square, coupling with the torsional angular momentum, P gamma square. And this is the Hamiltonian that many people use to fit the spectra. Now, what is the result of that? The result of this is that when the benzene water spectrum was published in 1993, a number of lines were able to be fit precisely to the ground state symmetric top, but there were a few striking lines which could never be fit exactly to any of the torsional motion quantum numbers. Therefore, we have to go back and rethink about it. Now, if this happens only with benzene water, it is unique to that. But it doesn't happen with benzene and water, but it happens with every other system which involves a similar symmetric top. So let me give you those things up. Those are, for example, sorry, let me quickly go to those. Those are examples of, say, the carbon-13 isotopically substituted benzene water. That's a slightly asymmetric top, but it's so slightly asymmetric that we can still consider this approximately as a symmetric top. Then what are the other complexes? Argon on one side, benzene in the middle, and water molecule on the other side. Argon, neon, krypton, therefore rare gases. This is a trimer. Three species, argon, benzene, and water. Then we have the hexafluorobenzene water. This is studied by different groups have studied all these things, and each one of them came up with the approximate torsional model. The approximate torsional model being that there is a torsional quantum number, and therefore this torsional quantum number has a symmetry of the species. This has a twofold symmetry because when water molecule appears the same way, this hydrogen goes over there and this hydrogen. Therefore, the torsional barrier due to water molecule is essentially doubly degenerate, but benzene has a 6-fold degeneracy. Therefore, this potential will have a 12-fold degeneracy. So these are things which have been used in fitting. This is the other example of hexafluorobenzene water, where now you see that the water molecule is inverted. Here, the hydrogen points towards the benzene ring. Here, the fluorine points, the oxygen points towards the hexafluorobenzene substituent. So these are all experimentally known structures through the microwave spectroscopy, but all the spectral lines could not be fit, and therefore what PRESENT did was to replace the torsional rotational model. Let me just quickly go back to what is called the L-type doubling model. So let me stop sharing and we'll show you what L-type doubling model is from my picture. Yeah, you can see me now, I guess. See, what happens is a symmetric top molecule has two degenerate bending modes. Therefore, the bending modes having the same frequency, degeneracy means same frequency, they can couple to the overall rotation of the, and if the bending mode is about this way, and if the bending mode is about this way, this is a degenerate example in the case of carbon dioxide, if you can think of, and these two bending modes, this side versus this side, both coupling to the angular momentum, which is about this, the molecule is rotating this way. Therefore, this is a clear, classic case of a coupling between all of them, leading to a vibrational or angular motion in a direction perpendicular to both of these. Therefore, the Coriolis coupling shows up in a very, very beautiful way. I'm almost done in another 5 minutes. The Coriolis coupling shows up very beautifully, and if you take that into account, the Hamiltonian is known as the L-type doubling Hamiltonian. The classic example for physics students is that two degenerate harmonic oscillators, one harmonic oscillator oscillating this way, another harmonic oscillator oscillating this way, these two with the same frequency generate what are called the Lissajous figures or a circular motion figures. That's the basic picture that you have for the coupling between harmonic modes. Now that is coupled to the overall rotation, and therefore what you see is what you are surprised to do, to see that the L-type doubling phenomenon, which was known for more than 40-50 years for a symmetric top Hamiltonian, introduced a different quantum number. It no longer treats vibrational angular momenta. They are quasi-rotational angular momenta. So we calculate all the matrix elements, and then we fit the spectrum. We are so happy to see that the spectrum, all the lines of benzene here, for example, the fit was done previously by one of my earlier students many years ago. All the observed lines, you can see that not all of them were fit, only a few were fit. But the moment the L-type doubling Hamiltonian is used, the rotational Coriolis coupling term is used, the fitting is 100%, absolutely 100%. And you can see the spectrum having every one of these lines being fit using the L-type doubling Hamiltonian. You can see that. The missing lines, now we are also predicting for the experiments additional lines that they can look at. These are the lines which are not earlier fit, but all these lines are now currently fit. This is a repetition. Now the process of fitting is slightly more involved. One has to calculate rotational vibrational matrix elements, and one has to program this, calculate the frequency, the energy levels, and then calculate the frequencies, and then fit them to the experimental rotational constants and rotational lines. Now, at the end of all of this, what happens? It's a very simple spectroscopic fit that applies to all the molecular system that we have studied, similar to the benzene water. In all of them in the past, a few lines have been dropped out from the fitting because they could not be fit by the torsional model. But now, present day, the student who is about to leave after doing all these things has found that every one of these spectra, about 7 or 8 experimental groups. This paper, which was submitted to Journal of Magnetic Molecular Spectroscopy, had a tough time. 2 revisions it went through, so many questions were asked. But at the end of that, the referee says, it's impossible to believe that this has happened, that everybody's spectrum is fit to a singular one Hamiltonian, which is different from all the 30 years of thinking that has happened in the field of microwave spectroscopy. Microwave spectroscopies are very, very precisely measuring, very precisely measuring experimental frequencies and fitting them to something like 3 or 4 levels of accuracy, kilohertz level of accuracy, when you are talking about 10,000 megahertz as a transition frequency. So I have the last the slide to tell you that we have also looked at these things from the ab initio point of view to see if the vibrational modes are relatively low frequency so that the excited vibration states will not break the complex. We have verified all those things. And towards the end, what I have is this one. You can see all the different molecules, CF4, H2O, which has a spectrum like this. CF4 is a spherical top with the H2O, CF4, H2O, a symmetric top. I'm done. I'm almost done. So the summary is that about 30 years of many different experiments, and we found out that the theory that needed to be useful for this is not what has been developed in the last 15 years or 20 years, but something that goes back to many, many years of a very simple symmetric top and the L-type doubling Hamiltonian, which have been studied by very, very previous spectroscopists like Hertzberg and Proto and many others. And the Coriolis coupling seems to be a natural way to fit all the symmetric top van der Waals complex spectra. And this was a fact that was, Arunan talked to me about this in 2001. At that time, I discounted him and I told him it's not possible for Coriolis terms to be present here because vibrationally excited states will not allow these molecules to survive. But then we found out over a period of time that these vibrational energies are very, very low bending frequencies, and they were never more convincingly demonstrated than by present here. And therefore, if you get, always look for a good student and never let the student come and tell you that he cannot do this. Tell him to go back and look at it. And finally, the credit for fitting this goes back to my student. And this thesis, Professor Arunan thinks, has solved about 30 years standing problem in the whole field of the microwave spectroscopy of the van der Waals complexes. Thank you so much. I could share with you other details, but given the time, I can only tell you what the phenomenon is and what the result is. The rest is subject to discussion. Thank you.
Thank you so much, sir. You are on time. Perfect. Thank you so much, sir, for wonderful talk on microspectra of benzene and water and the substituted benzene and water. Thank you so much, sir, for exciting talk. So now we'll move to the next speaker. So the next speaker is another distinguished professor, my guru, Professor G. Mugesh, from Department of Inorganic and Physical Chemistry, Indian Institute of Science, Bangalore. He is currently the chairman, now it is called Dean of Chemical Science Division of IISc Bangalore. His main research interest is developing synthetic small molecules and or nanomaterials for various therapeutic applications of complex diseases, mostly caused by oxidative stress. So Professor Mugesh has received many awards, to name a few: Shanti Saurabh Sarnajanti Fellowship, Asian Rising Star, and he is the fellow of all the academies, including Indian Academy of Sciences, the National Academy of Sciences, Indian National Science Academy, the World Academy of Science, and the Fellow of Royal Society of Chemistry. He received Shanti Saurabh Bhatnagar Prize in 2012, Info Prize in Physical Science in 2019, and the J.C. Bose National Fellowship in 2020, and many more accolades. So with this brief introductions, I'll request Professor Mugesh to deliver his talk on thyroid hormone action. Yes, sir, it is coming. Sir, you have to.
I think
Can you hear me?
Unmute. Now it's okay.
Yes.
Yeah. Good afternoon to all of you. Take this opportunity to thank IIT Tirupati Chemistry Department, Professor C.P. Rao, and other organizers for inviting me to give this talk. Unfortunately, could not come in person. In today's talk, I will be talking to you on one particular aspect at the chemistry-biology interface. How does a single atom change alter the thyroid hormone action and membrane transport? So throughout my talk, I will be talking to you on one atom change and how this one atom change can affect the biological system, the biological processes. If you look at this periodic table, there are 28 elements which are biologically important, approximately 28 elements. I'm going to focus on the colored ones, group 16 elements and group 17 elements. If you look at group 16, oxygen group, move down the periodic table, oxygen, sulfur, selenium and tellurium. Oxygen is everywhere in biological systems. All organic molecules have oxygen. Sulfur is present in proteins, amino acids. And go to selenium, it becomes very rare. But in human body, there are 25 proteins that contain selenium in the form of selenocysteine. And without selenium, one cannot survive. And these 25 proteins, including many proteins in human body, thyroid glands and oxidative stress, controlling oxidative stress and so on. But the nature somehow avoided using tellurium. If you see tellurium, it's a toxic element to biological systems. You go to the next group, group 17 or the fluorine group. Nature avoided using fluorine, chlorine, bromine in human body, but it chose iodine. And this is intriguing. And looking at the selenium and iodine, there seems to be a diagonal relationship and how this works in human body. So I'm going to explore in my talk and how these two elements are related. And I will start with a very fundamental process, and I'm sure all of you are familiar with this cycle, which is known as the frog cycle, where the tadpole is turning into frog by a process called metamorphosis. And the student starts studying this from 6th grade or 7th grade, which is a frog cycle. The tadpole is turning into an adult frog in this process. But if we grow this frog, these tadpoles, in a water which does not have iodine, then the tadpole will never turn into frog. It remains tadpole and die. And this is an amazing transformation which is mediated by iodine and an iodine containing compound known as thyroxine. And a very unique compound in human body. Thyroxine T4, if you look at the T4 structure, you can see there are 4 iodine atoms. That's the reason this is called T4. The 4 indicates the number of iodine atoms in these molecules. It has amazing function in human body. And thyroxine was isolated in 1914 by Kendall from pig thyroid gland. So he was successful in isolating 7 gram of T4 from 3000 kilogram of pig thyroid gland. He won Nobel Prize in Physiology and Medicine in 1950. If you look at this molecule, how it is synthesized in human body, you can see why we need iodide, because iodide, we take iodized salt, and food without iodine lead to iodine deficiency and thyroid gland malfunctions, thyroid gland problems. The iodine is transported inside the cells by sodium iodide symporter, and you can see that iodide is taken outside these cells, which are called thyroid follicular cells, and then the iodination of tyrosine residues in protein takes place by an enzyme called thyroid peroxidase, which is a heme containing protein, which introduces iodide into the protein through the tyrosyl residues. And once multiple tyrosyl residues are iodinated, then there is another process called phenolic coupling reactions, where 2 iodinated tyrosyl residues are coupled together to form T4. And then this, once the T4 is produced, it undergoes endocytosis, and then proteolysis leaves T4. And then once this thyroxine is synthesized inside the specific cells, it's taken outside the cells and they enter into the circulation. And this is a very, very specific process, very, very important process. And this happens only in thyroid follicular cells, in thyroid gland. And this is the reason, if somebody undergoes a surgery and the thyroid gland is removed for some reason, the person should take synthetic thyroxine throughout the life, because no other parts of the body can produce thyroxine. And in my talk, I'll be talking to you on a single atom change. This is thyroxine. The entire body metabolism depends on the amount of thyroid hormone produced. And if you look at the structure of thyroxine here, there are 2 iodine atoms in the outer ring and 2 iodine atoms in the inner ring. And all iodine can be removed. You can see if you remove iodine from the outer ring, it produces T3, 2 iodines in the inner ring and 1 in the outer ring, which is biologically active. If you remove the iodine from the inner ring of thyroxine, it produces a reverse T3, which is biologically inactive. Both the processes are equally important, because the production of T3 activates the thyroid gland and all the harmonic actions, and the removal of iodine from the inner ring to produce a reverse T3 control the thyroid hormone level in the human body. If this process is more, it leads to hyperthyroidism, and if this process is more, it leads to hypothyroidism. So therefore, a perfect control of thyroid hormone activity is necessary to control the human function. And this is the 1 atom change, and removal of 1 atom actually determines life or death. And that's the reason why this is regioselective, and it's important. And these reactions are catalyzed by a set of enzymes called iodothyronine deiodinases and IDs. ID1 and ID2 remove iodine selectively from the outer ring to produce T3, and ID3 and ID1 removes iodine from the inner ring to produce reverse T3. And all 3 enzymes are selenoenzymes. So they contain selenocysteine in the active site. Although they contain selenocysteine active site, they are regioselective, and which is important. And if you look at the structure of selenocysteine, and this is similar to serine and cysteine here. Again, 1 atom change. In serine, it is oxygen, cysteine, it is sulfur, and in selenocysteine, it's selenium. And 1 atom change lead to a lot of changes in the reactivity, because the pKa of a selenol group, which is 5.2, much lower than the pKa of a thiol group, which is 8.3. Again, that is lower than the pKa of a hydroxyl group in serine, which is around 13. And many years, people tried to mimic the function of this by synthetic compounds, because chemists are interested in functionally mimicking the enzyme with the small molecules. But this is it's a very difficult process to make functional mimics for iodothyronine deiodinases, selectively remove iodine from thyroxine. And we worked on this for several years. It took 10 years for us to come to this level. I'm leaving all the attempts that we made to remove iodine selectively from thyroxine. I'm going to talk about only the success that we had. So we looked at the enzyme active site, and the structure of the enzyme is not available. People made three-dimensional models to understand how thyroxine binds to the active site. If you look at the amino acid sequences in these three proteins, the U represents, the U is the selenocysteine, location of selenocysteine. And then we looked at the amino acid sequence, the next to the selenocysteine residue, there is a threonine, and then there is a cysteine. So we looked initially, if you have a thiol next to the selenol, whether we will be able to remove iodine from thyroxine. So till this stage, we tried to synthesize several selenium compounds, hundreds of them, and tried to remove iodine from thyroxine by using these selenium compounds, but without any success. None of the selenium compounds was able to remove iodine, and it's quite stable molecule, and removing iodine from thyroxine is very difficult. So we thought about this structure like something like this. So we introduced a selenol group in thionaphthalene here, and a simple reactions using a butyllithium mediated lithiation reactions and introducing selenium, we get the selenyl sulfide in 52% yield. So we reduced this selenyl sulfide and then got this one thiol and one selenol. And when we treated this with thyroxine and followed the reactions in phosphate buffer at pH 7.5, 37 degrees Celsius, physiologically relevant conditions, and we followed the reaction by HPLC, you can see that this peak is going down with the time, and this peak is coming up with the time. And this was the first time in 10 years we could see a new peak in HPLC. All the time we were able to see only the thyroxine peak, nothing happened to that. And we were surprised to see this, only one peak in this case, and we analyzed the product, and this happens in physiologically relevant conditions. And we found that it produces a reverse T3, and that means this compound selectively remove iodine from the inner ring of thyroxine to produce a reverse T3, and T3 also again inner ring iodine is removed and it produces T2. So it doesn't remove outer ring, and also it stops after one iodine removal. It's highly specific and quantitative conversion of T4 to T3. It was surprising because if you look at the X-ray structure of T4 here, all iodine atoms are exposed. The outer ring iodines are the phenyl ring of this is perpendicular to the inner ring. It's about 90 degree perpendicular to this. All iodines are exposed, but still these compounds remove one iodine. If you increase the concentration of these compounds to 5 equivalent, 10 equivalents, nothing happens to further to reverse T3 or T2. It stops after removal of one iodine atoms. And again, we did single atom modifications. We took two thiols in the 1,8 position, which are known as the peri positions in naphthalene rings. And we substituted one of the thiol with the selenol, just one atom change sulfur to selenium. And then again, one more atom change, this sulfur to selenium. So you can see the activity change. When we have two sulfur atoms, it is inactive. Changing one sulfur with the selenium, you can see that there is an enhancement, 12-fold enhancement in the activity. But remarkably, when we change the second sulfur with the selenium, you can see that there is 91-fold enhanced in the activity, which can be further enhanced by putting a basic amino group here, which can deprotonate the thiol selenol, enhancing the activity. When you block the second selenium with the phenyl group, or this one, we don't get any activity at all. So this indicates that both the selenium atoms, or at least one selenium atom, is important for the activity. So we wanted to see where increase in the reactivity may change the selectivity, because that is known in organic chemistry. The reactivity may change the selectivity, but in our case, whether we use two thiols, one thiol, one selenol, or two selenols, the increase in the reactivity does not change the selectivity. It remains remove only the inner ring iodine, and it stops after removal of one iodine. So we wanted to see what is the molecular mechanism of the selective removal of iodine. And when we know that in organic halides, the electron density is anisotropically distributed around the halogen atoms. And then, you could look at the iodine atoms, and this is called the sigma hole. You can see the tip of the halogen atoms, and this can actually non-covalently interact with the electron donors, forming a halogen bond. And this positive region is termed as a sigma hole, and people call it as a sigma hole interactions or halogen bonds. And the side of the halogens can be involved in hydrogen bonding, because the hydrogen bonding with the hydrogen bonding acceptor, and in this case, it acts as a halogen bond donor, and with the halogen bond acceptor, this can form a halogen bond. And the sigma hole increases when we move from chlorine to fluorine to bromine to iodine. And in the case of iodine, the sigma hole is more. So therefore, the positive potential along the CX axis increases from fluorine to iodine. And this may be the reason why nature chose iodine, leaving fluorine, chlorine, and bromine, because iodine can form much stronger halogen bond with the halogen bond acceptor or electron donor. And we calculated DFT structures, DFT calculations, and found that all the iodine atoms in thyroxine, in fact, has the sigma hole. And the iodothyronine deiodinases, the enzymes that remove the iodine selectively, have selenocysteine in the active site. And you can see that the residues, selenocysteine residues in the active site. And selenium is a strong halogen bond acceptor. And it is an ideal combination of a selenium and iodine, which lead to the removal of iodine. So we thought that halogen bonding may be responsible for the deiodinase activity. I'm skipping all the details that NMR, selenium NMR that we have done, and in solution structures and so on. I will come to the theoretical calculations, which give very interesting observations. If you have only one selenium or one sulfur, the lone pair interacts with the sigma star antibonding orbital of the carbon iodine bond, and it forms a halogen bond. You can see that 23.4 kilocalorie per mole, and this just to form a halogen bonded adduct, and it stays there. And same thing happens with the sulfur, not much difference between selenium and sulfur. But what happens when you put an additional atom in the 8 positions? In this case, it is sulfur. In this case, it is selenium. So what happens initially? The lone pair interacts with the antibonding sigma star orbital of the carbon iodine bond, leading to an elongation of the carbon iodine bond. And the sulfur becomes much closer to iodine by halogen bonding. And these interactions actually weaken the carbon iodine bond. So it elongates the carbon iodine bond. But it's not enough to cleave the carbon iodine bond. So when you have a second atom here, the lone pair on the sulfur again interacts with this sulfur, strengthening the halogen bond. This leads to further elongation of the carbon iodine bond. In the case of selenium, which can donate the electron density to the antibonding orbital here, and then when this selenium donates electron, it becomes positive, slightly positive. At that time, it starts accepting electron from this selenium, forming a selenium-selenium covalent bond here. And this selenium-selenium covalent bond formation is accompanied by the cleavage of the carbon iodine bond here and simultaneous formation of a selenium iodine bond here. And this is responsible for this unusual activity. In this case, then we proposed a mechanism where the lone pair on the selenium initially interact with the iodine through the sigma hole, weakening the carbon iodine bond. And then when it becomes slightly positive, the second selenium starts interacting with this one and leading to the complete cleavage of the carbon iodine bond and the removal of reverse T3 and forming a diselenide, which can be reduced to the diselenol form by using reducing agents like DTT. And this is a unique mechanism that we proposed. And what we found later on, the nature of chalcogen atoms play a very important role. We thought we have done with sulfur. Sulfur is not active and selenium is active. What happens? You move down the periodic table and go to tellurium. So what we did, we put a tellurium and a sulfur here. We can reduce this sulfur tellurium bond by using reducing agent and get a 1-thiol, 1-tellurol. And then when we carried out the deiodination reactions, and we followed the reaction by HPLC, and remember the previous HPLC I showed, very clean HPLC, only one peak, new peak appeared in the HPLC. But in this case, there are multiple peaks. So that means there is something more than one deiodination which is taking place in these reactions. So we analyzed all of them. We collected the fractions for all the compounds, and we analyzed by HPLC and mass and NMR. And we found that the T4 undergo deiodination to produce a reverse T3. That's what we saw in the case of selenium. But also, tellurium compounds remove iodine from the outer ring to produce a T3, and both of them undergo further deiodination to produce T2, then T1, then T0. So we end up in this compound where there is no iodine atom present. So that means sulfur is too less reactive, selenium is the optimum one, but move down to the tellurium, it's too reactive to control the selectivity. And this again confirms that why nature stopped at selenium, did not go to tellurium, because it's too reactive to control the selectivity in this case. And this is not good in biological systems. So therefore, in most of the biological reactions, you will see that it's selectivity which is more important than the reactivity. And many enzymes act at very, very low activity level, and some enzymes act extremely fast. And there is a reason for it. And how do these compounds get into the cells? So that is the next question we asked. And these compounds get into the cells by using a transporter called MCT8. And this is the plasma membrane transporter. When the T3 or T4 comes through the blood flow and enter into the cells through MCT8, this is called monocarboxylate transporter 8. And this is expressed in brain. The brain function MCT8 is very, very important. And the MCT8, the mutations in this lead to diseases. And this is called hypothyroid brain. And the genetic defect is known as Allan-Heldon-Dudley syndrome. And this is known since 1944 without knowing its actual cause. Some of the symptoms for this disorder: normal to slightly elevated thyroid stimulating hormone, elevated T3 and reduced T4, and normal looking at birth and for the first few years, but cannot walk independently and become wheelchair bound by adulthood, are a very, very important receptor in the brain which transport thyroid hormone inside the cells. So what we thought, that means the halogen bonding or the halogen atoms is playing an important role in taking these compounds inside the cells by MCT8 transporter. We prepared a fluorescent probe like this, introduced the halogen atoms. We have a hydrogen, chlorine, bromine or iodine. We studied the cellular uptake. So how these compounds are taken up by mammalian cells. So what we did, we studied the fluorescent property. That's the reason we used the fluorophore here. And what we found very interesting, when we have iodine here, the cells take up the compounds more. You can see that when it is hydrogen, no cellular uptake or very small uptake. When we substitute the hydrogen with the chlorine, 15% uptake. Substitute the hydrogen with the bromine, 38%. When we substitute the hydrogen with iodine, 98% uptake. So that means all the compounds that we add to the cells are taken up by the cells. And a lot of studies we carried out, and finally we found that in fact these compounds get into the cells through the MCT8 transporter, which are specific for thyroid hormones. And what we did further, can we put a protein inside the cells? These are all small molecules, they can get into the cells quantitatively. But what about proteins? So we chose green fluorescent protein. We substituted a tyrosyl residues, hydrogen atoms on tyrosyl residues by chlorine, bromine, and iodine. And these are called unnatural amino acids. And you know, when one atom is changed in an amino acid, the nature doesn't accept it. And we need to modify the amino acid, the synthetase, tyrosyl amino acid synthetase, to accommodate this, which is known as the expanding the genetic code by mutational studies. We mutated the synthetase, which is specific for tyrosines. And these are the mutations that we have done. And I don't go into the details. And this is the process where we express the proteins in the cells. And then we get the substituted one with the chlorine, bromine, and iodine. And we have actually expressed, these are the green fluorescent protein you can see expressed. This is the gel electrophoresis. We can isolate this protein, purify them. We can get a very clean mask of these proteins. And then we carried out the halogen mediated cellular uptake. You can see this is the GFP, which having hydrogen, chlorine, bromine, iodine. You can see the cellular uptake increases when one atom is changed. Hydrogen, no uptake. Chlorine uptake is more, bromine further increase, and iodine the maximum. And we also have figured out how these proteins enter the cells through caveolin-mediated pathway, we can release the protein in cytosols by using endosomal lytic peptides. And in this case, we have shown for the first time that in a 28 kilodalton protein, by changing just one atom on the surface, we can actually make these proteins enter into the cells. We believe that this has a great applications in medicinal chemistry and drug development, because the cellular uptake of the protein is a major problem in this case, in using protein as a therapeutics. And with this, I would like to thank my former students, Dabasis Manna, Raja, and Santanu Mandal. Most of the work I presented from them. And also I have students working in various areas. I take students from both chemistry and biology, and we have labs to carry out both the works. And as the introduction, Professor Ganesh and others mentioned about working the interfaces, and we work truly at the interface and trying to use our standard chemistry for some of the problems. And I thank all of them, the funding agency, and I thank you for your attention. So I hope I have taken just 24.5 minutes. Thank you very much.
Thank you, sir. You are on time. So thank you so much for a wonderful talk on thyroid hormone chemistry. Thank you so much, sir. So the next, we'll move the last lecture of this session by another distinguished professor and a leading electrochemist in India, ever energetic and enthusiastic Professor Vijaya Mohanan K. Pillai from our neighboring institute, IISER Tirupati. He is currently the Dean and R&D of IISER Tirupati and the Chairman of the Chemistry Department at IISER Tirupati. He was a former director of CSIR Sikri, Central Electrochemical Research Institute, and the director in charge of CSIR NCL Pune. So Professor Pillai has received many notable achievements, a list a few. CRSI Silver Medal 2020, CRSI Bronze Medal 2004, and Scientist of the Year Award by NCL Research Foundation 2003, National Prize for Research on Energy Materials and Devices by James CASR. He is the Fellow of Indian National Science Academy, Indian Academy of Sciences, Bangalore, and Maharashtra Academy of Sciences 2004. So his research interests are batteries, fuel cell, bioelectrochemistry, and electrochemistry, electrochemical sensors, etc. I request Professor Pillai to enrich us with his huge experience on developing 2D materials and their various applications like single electron transistors, sensors, and developing energy storage devices. So today he will talk on heteroatom doping of phosphorine quantum dots at room temperatures. So I'll invite Professor Pillai for delivering his lecture.
Thank you, Gauri, for a very warm introduction. Good evening. Ladies and gentlemen, it's my pleasure to be a part of this wonderful seminar. And at the outset, I would like to thank Professor Fullarao and Professor Satyanarayana for inviting me for this National Symposium on Recent Trends in Chemical Sciences. And you have just heard a fascinating account by Professor Mukesh about how one atom changes in a molecule can be a question of life or death. I'm also going to talk about a change of one atom, but not on a molecule, but on a material. Of course, there is no life or death here. It is more related to applications. Human beings have been always fascinated by materials, right from Stone Age to Internet age. We are always fascinated by different types of materials. I thought it may be important for me to talk about one type of materials. We talk as two-dimensional materials. Dimensionality is an important parameter because when we want to use materials for our benefits, we want to tune materials. Professor Mukesh talked to you and also many others, Rangarao, Professor Ganesh, they all spoke to you about the power of chemistry. We can manipulate matter at the atomic level. Atom of iodine, you are changing. Now you see what type of influence on life itself. In a similar manner, I would be talking more about two-dimensional materials.
Excuse me, sir.
Yes, please.
Yeah, sir, we have one request. Sorry to disturb you. Sir, can you adjust your video because it's a live is going. Excellent, sir. Excellent. Thank you so much.
Good, very good. I am slightly out of focus, right? Yeah.
Thank
So,
you, sir.
yes. So the point is, why are we interested in two-dimensional materials? We are talking about normal materials, three-dimensional materials. We are going to talk about two-dimensional materials. Some of these examples are shown here. Just one layer of materials, atomically thin layer. I'm sure all of you have heard about graphene. Then we have got such fascinating materials. Transition metal dichalcogenides. We also have phosphorine, stannine, bismuthine. So what is so interesting about two-dimensional materials? From a physics point of view, when we talk about one layer of materials, there is nothing on top. There is nothing below. That means you don't have electric screening. When there is no dielectric screening, we'll talk about in-plane electronic motion. So when the carriers, whether it is electrons, whether it is excitons, any type of carriers, sometimes it could be for thermal conduction by phonons. So carriers will move only in this plane. And due to that, some fascinating properties, exotonic properties will come into picture. So we talk about such 2D materials where the motion in that plane is not impeded even by impurities. We talk about Dirac fermions, carriers will move to very high mobility. So for electronic applications, optoelectronic application, field effect transistors, you will see some important benefits, fast switching, less power consumption. So two-dimensional materials, when we talk about, we also from a chemistry point of view have a lot of benefits. We can look at the edge states. Edge states can be controlled. We can functionalize these 2D materials, make them soluble in organic solvents. Sometimes we can make them soluble in aqueous medium. So these are all the benefits. I will talk to you about, I will not talk about all these 2D materials. Only one example I will talk today about phosphorine. Phosphorine is a two-dimensional analog of phosphorus. I am sure as students of chemistry, most of you or all of you must have heard about phosphorus. Professor Mukesh talked about a diagonal relationship between iodine and chalcogen site, selenium. We extend the diagonal relationship, then we come to phosphorus. You can see now we are diagonal stretched. Phosphorus has been of great relevance from time immemorial. Phosphorus has a very interesting history. Phosphorus is considered as a glowing element because sometimes it used to glow. So the word itself, phosphor, means bearer of light, came out. But what is more fascinating is, initially people thought that phosphorus is something which is related to life aspects. In fact, 1675, somebody isolated phosphorus from human urine. So the stale urine has a yellow color. This is a time of alchemy. People were fascinated to transform element. Everybody wanted finally to make everything to gold. So this is the time of alchemy. In 1675, somebody observed that stale urine has yellow color, gold has yellow color. So they thought that it is possible to transform stale urine into gold. They collected 50 buckets of urine, kept it there, so many concoctions. Eventually, it gave a waxy material which gave rise to phosphorus. Starting objective was to transform all this to gold, you can imagine. But from human urine, phosphorus was isolated. Of course, it was very expensive, 300 pounds for 1 ounce. This was, we are talking about 1670s. And phosphorus was not known as an, and if somebody wanted phosphorus for various applications, how will you get it? How much urine you need for isolating phosphorus? So what happened is, officially, soldiers were asked to collect all the urine, give back, and then they isolated phosphorus. This was something which is much, much earlier to Carl Scheele. Carl Scheele came into picture. Scheele is the one who first found a method of preparing phosphorus from rock phosphates. And Sheila's story is also very interesting from to any general chemistry student, because Scheele is also known as hard luck Scheele because he had no luck at all. He had 8 elements, several elements, chlorine. Credit went to Davy, who invented chlorine after 36 years. Fluorine he invented, manganese, molybdenum, tungsten, nitrogen, oxygen. All these elements were first invented by Scheele, but Scheele did not get any credit for any of these elements. Oxygen was invented by Priestley independently after 2 years. So everybody thought that Priestley is the one who invented oxygen. You can imagine. And Scheele died at the age of 43. At 43 years old, he died. He was found dead in his laboratory. in his workbench. You can imagine, one reason people say that Chile used to take all his chemicals. He was a passionate scientist. Anytime he does anything in the laboratory, just taste a little bit, very nice taste, bad taste. So he had acute poisoning, and that is one of the reasons why at the age of 43 he died. Anyway, let us come back to phosphorus. Phosphorus, Sweden became a matchbox making country primarily because of Chile. Chile is the one who found the process of making phosphorus, black phosphorus, red phosphorus, white phosphorus. From a two-dimensional perspective, phosphorus has certain unique behavior. All of you know that phosphorus has a pucker structure. That means you have two pp distances. One in the first, there is a slight bending. These two pp distances are different. And this is important when you look at the band structure. Why is it important? Because we are talking about phosphorus, layer structure, delaminate it, take one layer of phosphorus as a monolayer. Sometimes experimentally monolayer is difficult, then we look at 2 layers, 3 layers for application point of view. Little more interesting if you can confine more quantum confinement. Remember, two-dimensional means electronic motion is confined in this plane only. However, there are edge states. These edge states can be controlled. Just like what Professor Mukesh spoke about changing one atom. Here I am going to change one phosphorus atom by nitrogen. We talk about nitrogen-doped phosphorus. Nitrogen-doped phosphorus as a monolayer. And when you look at as a zero-dimensional quasi particle, then what happened is nitrogen-doped phosphorine quantum dot. So compared to two-dimensional phosphorus, we are talking about a quasi zero-dimensional. We have one more confinement coming into picture. Little more interesting because we have a band gap which can be tunable based on size. Size means we talk about the height dimension, z-axis. Lateral size may be 20 nanometer, 30 nanometer, but height is something which you are talking about 1 layer, 2 layer, 3 layer. More than 3 layer is not interesting. Now, if you look at from a structural point of view, we have a very strong in-plane covalent bond. PPD bonds are very strong, but in between the layers, we have a very weak van der Waals force. That means both these forces are very important for applications. So if you want to make device out of this, we have several applications. Phosphorine as a two-dimensional material or phosphorine as a quantum dot. We can have several applications in energy storage. We can make stretchable, bendable power sources with the phosphorine. We can make layer by layer assembly of phosphorine with respect to certain polymers to make a composite. Phosphorine, although 1914 black phosphorus was first isolated, it was used for the first time as a field effect transistor in somewhere 2014, after 100 years. After 100 years only people could experimentally measure that you get very high mobility. We talk about ballistic transport. This gives rise to an entire set of applications. These talk also about twistonic applications. One phosphorine layer on a graphene layer and slightly twisted. When 1.1 degree angle comes, certain magical things happen. And because of that, there are applications in electronics, violetronics, twistonics, two-dimensional electronics. We use several fashionable terms, but actual interest is the electron transport in this plane. Phosphorine is an interesting system. Some applications we can tune the band gap by doping. So I'm going to give you some examples where phosphorus is doped by nitrogen. Nitrogen doped phosphorine quantum dot. I'll be using PQD for phosphorine quantum dot and NPQD for nitrogen doped phosphorine quantum dot. Several applications. So doping is concerned, you can dope it by alliovalent or isovalent material. Accordingly, you can see electrical properties, mechanical properties, thermal properties. They also can be controlled. And again, you can also do functionalization, attach several materials. For energy storage and electronics, there are intrinsic benefits. For example, electron transfer is very fast, short diffusion length scale, edge states can be controlled in a selective manner, and in general, phosphorine is a good example of a 2D material with all the remarkable features of 2D material. What are the remarkable features of 2D material? You can look at it. 2D material spans one side, you have got a very hard insulator, no carriers at all, hexagonal boron nitrate, 5 electron volt band gap. You come to little lower materials, narrow band gap semiconductor, and then you have the other extreme is semi-metallic systems or graphene, which is highly conducting with zero band gap. So zero band gap to 5 electron volt band gap is something which you can tune. And when you talk about electronic materials, the entire electronics can be made by only material. 2D insulator, 2D interconnect, and 2D semiconductor. So this is what we talk about 2D electronics. And again, I will not go to details. There is some noise. And what is interesting is you can make one layer. On top of that, you can make another layer, and then you will see that in some certain twisting angle, the entire resistance disappears. This is why people are so much interested in 2D electronics. You can see now there is a plot of mobility versus on-off ratio. You can get very high on-off ratio, 10 power 9, and some of these are mechanically robust when we talk about one plane alone. Of course, some of these materials, there are issues about degradation, but you can see now triangle of a twistonic system. For example, here you have an MOS2 2D layer. On top of that, you have a WS2, VS2. These are all interesting because of its electronic band structure. You can play with several such structures. Heterostructures can be made. This is an example where graphene sitting on hexagonal boron nitride, and you can rotate them. Accordingly, you can control their electron transport behavior. So 2D materials like phosphorine is also important because of the asymmetric band structure. When I say asymmetric band structure, start with the monolayer of graphene. Monolayer of graphene, you can see now the band structure is interesting. I mentioned you about the band structure because energy and momentum have a relationship, linear relationship. Look at the valence and conduction bands. You can see now there is a symmetry here, but when you come to a bilayer graphene, the energy momentum relationship is linear here for monolayer graphene. When you come to bilayer, it is parabolic again. And then you can come to hexagonal boron nitride where you remove the symmetry because our carbon is removed and you have got boron and nitrogen. So you get a very high band gap. Coming to transition metal dichalcogenides, something much more fascinating from an electronic structural point of view. Look at the valence band and conduction band. Conduction band, there is a splitting. This splitting is very important because of the spin polarized bands. So the spin orbit coupling gives you unusual properties. This gives rise to even exotic magnetism for type of transition metal dichalcogenides, molybdenum sulfide, molybdenum selenide. It is also possible to make a Janus monolayer. That means molybdenum sandwiched between sulfur, MOS2, but instead of that molybdenum, one side sulfur, other side is selenium. So these are all interesting because the properties are not very well understood, not very well known. Monolayer of molybdenum sulfide, you have a indirect band gap, you have a bulk material has an indirect band gap. When you make monolayer, there is a direct band gap. So the band gap tuning is very important. When you come to phosphorine, there is an asymmetry. I mentioned to you two types of PP bonds. When you look at the band structure, this is extremely important because effective mass on x-axis and effective mass on y-axis, there's a big difference. 15 times more effective mass. That means this asymmetry will be translated into new application. Stress can be measured. You can even get piezoelectricity by looking at one layer of phosphorine. So we don't know much of the implications, but phosphorine is interesting because of this type of unusual electron transfer behavior. Band gap can be tuned in several ways. Band gap can be tuned in such a way that you take only monolayer to bulk. You see, for example, you have a bulk phosphorine, but that is called black phosphorus. You have something like, you have 0.3, very narrow band gap. With a monolayer, you have 2 electron volt. When you go to and make heterostructures, you can see again, band gap can be changed. So monolayer to bulk material, then you make heterostructures with graphene or with the TiO2. Then come to doping. Our main topic today is doping. You can dope with carbon, fluorine, boron, aluminium. Accordingly, you can control the band gap from somewhere very close to 0 to almost 3 electron volt. Intrinsic band can be controlled by edge structures. You have 2 types of edge structures, zigzag and armchair. They also, the number of such, the density of such edge states can be controlled by how do you prepare. Sometimes you prepare by mechanical exposure, sometimes you prepare by laser method, sometimes by you do ultrasonication. So based on what type of methodology you use to prepare phosphorine, you will be able to control some of these edge structures. Zigzag, cliff, armchair, accordingly the band structure changes. Lastly, you can do functionalization. You attach an OH group or a hydrocarbon group, accordingly you will get different type of band gap. So band gap can be tuned by number of layers, shape, as well as states. And we also can functionalize, we can have also doping. You can see now how many ways are there for you to tune this material. Tunability is very important for optical properties, optical transport. This is why we are talking about tuning phosphorine for applications. We have been working on 2D materials for almost last 10 years. Our major work was about graphene. preparation of graphene by an electrochemical route is something which we did. And what was more interesting was one step we could use to prepare as well as dope. That means at room temperature, we can dope these type of 2D materials. Conventional way of making these materials at high temperature using chemical vapor deposition, sometimes pulse laser deposition, there are limitations. If you use chemical vapor deposition, most of these 2D materials will show substrate dependent behavior. You prepare on cobalt 111, you get one properties. Remove the cobalt, sometimes they will have wrinkles. They may not be even stable. You prepare them Cu 111. So based on the substrate orientation, based on the nature of substrate, physical properties, chemical properties, all that will change. We prepare these materials by electrochemical route where the doping can be done at room temperature. For example, if you have a nitrogen containing solvent which decomposes or nitrogen containing supporting electrolyte, during the electrochemical preparation, for example, in this carbon nanotube, unzipping happens, carbon graphene quantum dots are prepared, you can dope at room temperature. A similar strategy we applied here for phosphorin. We take black phosphorus, you can see the structural transformation of black phosphorus to phosphorin quantum dot. You can of course use red phosphorus, white phosphorus. It doesn't make any difference what type of phosphorus you want to use. Black phosphorus is thermodynamically a little more stable for us to change it. Otherwise, you may have to convert that into black phosphorus. You can see the interlayer gap, which is 0.53 nanometer. Two types of phosphorus bonds are very clearly shown here. And then we coat this on a substrate, apply electric field, almost like -2 volt for 24 hours in presence of certain electrolytes such as perchlorate. You will see after this small phosphorin quantum dots are formed. So phosphorin quantum dot PP distances are slightly expanded. Even the interlayer gap is larger here, and you can tune the size based on the magnitude of electric field or the voltage gradient plane, the time, as well as the type of salts you use in solution. For example, we could make 7.8 plus or minus 1.6 nanometer phosphorin quantum dots. You can see black phosphorus CEM shows you several thick layers of morphology, while when you have PQD, phosphorin quantum dot, there are small quantum dots. The active strain is very important here because you can make them as strain sensors and also a field effect transistors. There is also interesting application like what Professor Rangarao talked about, reduction, electrocatalysis. Phosphorin also shows interesting applications for electrocatalysis. Structural transformation is something which is puzzling because black phosphorus being you can see in the orthorhombic structure of phosphorus, black phosphorus you take the powder X-ray, you will get all these planes 132, 060, 040. When you make as a phosphorin quantum dot or nitrogen doping, here we have done nitrogen doping in one step, you can see, but if you just take phosphorin quantum dot, you will see most of these planes have vanished. Maybe sample is very thin, 1 layer, 2 layer, 3 layer. But more puzzling is this 040 plane is shifted. And you can also look at by Raman. Raman will also be revealing to look at what type of transformation happens to the PP bonds, both in plane bond as well as on the edges. We also did some density function theory calculations because some of these phosphorin quantum dot, when the size is bigger, they all degraded based on the availability of oxygen. So the DFT was looking at the structure of phosphorin quantum dot, what type of structural distortion can happen on phosphorin quantum dot, with of course several assumptions. Assumption number 1 is that we take only monolayer. Assumption number 2 is that oxygen comes on the edges, plain oxygen doesn't come at all, and then we add slowly small amount of oxygen, 0.5%, 1%. So oxygenated and non-oxygenated PQD, there's a big difference in stability. And most importantly is you can also calculate the IR bands. For example, you can look at the P double bond, O band, the stretching vibration can be calculated theoretically as well as experimentally, and we can compare. So these all helped us to characterize the phosphorin quantum dot. We'll skip all the details about the calculations for this. What is interesting is doping. At room temperature, when you do phosphorin doping or nitrogen doping on phosphorin, we can use actually 2 methods. One is the solvent, a solvent such as DMF, which decomposes to give nitrogen containing groups, or we can use a tetraalkyl ammonium salts. Please remember that black phosphorus is there, several layers, and you cathodically exfoliate them. So if you keep the potential, we can do galvanostatically or potentiostatically. If you keep a potential constant, at that potential, if the solvent decomposes, or if we know that supporting electrolyte decomposes, then nitrogen species are produced. These nitrogenous species will go to the edge states and nitrogen could be doped on this phosphorin quantum dot. For example, what I have shown here is nitrogen doped to phosphorin quantum dot of sizes. The size difference can come due to either the time or the electric field, or sometimes you can different type of solvents. For example, here the size difference comes because of the changing of solvent. One case it is acetonitrile, in another case it is propylene carbonate. So the size tuning in this experiment depends on parameters such as you can control the electric field, you can control the time, solvent, and temperature, and the counter ion, what type of counter ion is used. Again, I will not go to details. You can see now the sizes of these quantum dots with various time, different type of electric field can be applied. For example, you can apply -2 for 2 hours, 3 hours. You will see some cases you can do 5 nanometer. Only thing is that you do experiments for various voltage gradient and various time intervals to get the size. In order to understand the mechanism, how PP bonds can be cleaved, first we looked at the electrochemistry, because this is an electrochemical way of transforming black phosphorus to phosphorin quantum dot. Black phosphorus voltammograms have been done many years ago. People have looked at it, various solvents. So black phosphorus, if you look at it, there is nothing very exciting. There's a small amount of oxygen. If it is present in the solvent, you will get oxygen reduction. Otherwise, you have a reversible couple. PP bond cleavage happens. It could be even reversible, mildly reversible. When you do several cycles, you will see that the conductivity enhances. You can see now, red one is after exfoliation. It has become 2 times, 3 times more. That is why the area of this peak, if you look at it, and also the reversibility has become slightly better after several cycles. NPQD and normal PQD, very interesting change. Number one, conductivity is much better for N-doped PQD. This is something which is also in line with what we know about other 2D materials. For example, nitrogen doped graphene quantum dot, conductivity becomes better. In a similar manner, we can see nitrogen can go to various sites here, but look at the red and the black one. You can see the black one has got different signatures. One of them is the PP cleavage, which is almost like, reversible. An IR correction, then only the reversible become very clear. But this is actually a radical formation. Phosphodoradical anion formation has been reported earlier. Now, if you do it on the anodic side, only problem is there is some degradation, because some of these forms a polymer, or some sort of a phosphor-based polymer is forming, which is not very well defined. But if you do several cycles, you will see that phosphorin quantum dot gives an electrochemical signature. The signature is very important. We are unable to distinguish what happens on the surface stage. Again, small amount of oxygen is there on the surface. IR and Diamond shows evidence for P double bond O on the edges. So these are all more details. Again, these details I will skip. How do you know you form a phosphorin quantum dot? We may have to take atomic force microscopy. AFM is very critical because the height profile of AFM is important. When you look at the height, you measure the C-axis and divide it by the interlayer distance, like 0.53 nanometer. We know that we get 2 to 3 layers of phosphorin quantum dot. Average size, again, depends on the solvent. We have made phosphorin quantum dots of various batches in propylene carbonate as well as acetonitrile. Propylene carbonate, because propylene carbonate is one of the electrolytes normally used for electrochemistry, especially non-aqueous media with respect to battery applications. So 7, 8, 6 different sizes of phosphorin quantum dots have been prepared. Optical properties are as expected. You have a very strong absorption, and the emission, you have got 3 bands corresponding to the homology and blue light emission. Blue light emission can be analyzed much greater details. Again, I will not go to details. I will tell that the Raman and the IR use. IR characterization tells you that some amount of PO bond stretching happens here. PO, PNH, NH happens only because of the nitrogen doping. Whether nitrogen the surface or nitrogen is on a dop, because we are talking about a monolayer or a 2-layer or 3-layer. That is why it is very difficult to distinguish whether it is on the surface or it is the lattice. That part is not very clear unless we make much thicker one. But when you make much thicker one, all these interesting properties disappear. XPS is also very important to look at the oxidation state of phosphorus. We say that phosphorin quantum dot. So we don't want to say that, look, phosphorus is 5+. We have to talk about phosphorus in zero valency state. We compare the XPS of normal black phosphorus as well as phosphorine quantum dot. Again, I'll skip all the details. We look at also the light emission. We use the time resolved fluorescence decay. You can see now, nitrogen doped to phosphorine quantum dot, you have only one decay, while normal phosphorine quantum dot, you have a bi-exponential decay. We have a collaboration with IACS Kolkata to give us some of these important parameters. Of course, the light emission, we look at time-correlated single photon counting experiments, species with 2 different lifetime. Again, these are all details I will skip. The luminescence properties and XPS clearly inform that we have got nitrogen doped in phosphorine quantum dot. So let me just summarize. I have been talking to you about only one 2D material, phosphorine. Phosphorine, two-dimensional sheets can be prepared, but much more important for application is the quantum dot of phosphorine, where the lateral size can be prepared, but the quantum confinement in z-axis is much more important. We prepare electrochemically phosphorine quantum dot in one step where nitrogen doping can also happen. But it's instructive for us to compare normal phosphorine quantum dot with the nitrogen doped phosphorine quantum dot, because the next step is not control the amount of nitrogen going into phosphorine quantum dot. Then you also use other heterogeneous dopants. For example, you can engineer this phosphorine quantum dot with fluorine, with boron, and other hetero elements which will not make the lattice unstable. Again, that means the size criteria is also very important for the quantum dot. So let me just compare these properties of normal phosphorine quantum dot with nitrogen doped phosphorine quantum dot. Nitrogen content is roughly of the order of 3%. Interlayer distance, normal phosphorine quantum dot 0.53 nanometer. Nitrogen doped phosphorine quantum dot, slight expansion has happened, 0.63 nanometer under similar conditions. So we are not talking about interlayer expansion due to anions or cations. In phosphorus bond length, slightly elongated for normal phosphorine quantum dot with respect to black phosphorus, while slight contraction happened for nitrogen doped phosphorine quantum dot. Raman spectral lines, you will see a little bit of paradoxical. Some of the bands are blue shifted, some of them are red shifted. Depends on whether we are talking in plane band or is slightly out of plane or towards the P double bond O at the edges. Photoluminescence quantum efficiency is 83% for phosphorine quantum dot. Doping as expected, quantum efficiency is much more, 88%. Remember that other phosphorine quantum dots or phosphorine 2D materials prepared by exfoliation and other methods, you will get only 20 to 30%. So the chemically prepared phosphorine quantum dot gives you much higher quantum efficiency. Photoluminescence lifetime 956 picosecond for phosphorine quantum dot. By nitrogen doping, you can see it become 875 picosecond. Radiative decay and non-radiative decay, also the comparison is given here. Phosphorine quantum dots are important for several applications. I did not touch the application at all. As Professor Engarao mentioned about electrocatalysis is very important application. Short diffusion length scale. Electrocatalysis in terms of both fuel cells, just like graphene nitrogen doped graphene can replace platinum. Phosphorine also has got interesting electrocatalytic properties. Somebody can even make a total battery of 2D material. 2D material for anode, 2D material for cathode, and 2D material layered polymeric structures as electrolytes. So these type of batteries will be flexible. You can see an example, just like sandwiches, different type of layered structures can be made by 2D materials. They are very strong, they are very robust. So let me just conclude. I've been talking to you about 2D materials, the fascinating materials due to interesting electronic structure. The properties can be tuned with respect to size, with respect to number of layers, with respect to dopant, as well as surface functionalization. Processing as thin film is also easy because you can functionalize them, organic solvent soluble, inorganic solvent soluble, etc. PP bond structures. That is interesting because we have calculation, we have Raman, we have different type of evidences, and we use XRD, XPS, and photoluminescence to calculate both pristine phosphorine quantum dot and doped phosphorine quantum dot. There are several challenges because some of these phosphorine quantum dots are not very stable. Photoluminescence after 2 or 3 weeks, you will see immediate degradation. Oxidation on the edges will create luminescent properties will disappear slowly. There are applications in electronics, electronics, and applications in energy storage for electrocatalysis for fuel cells, batteries, supercapacitors. We are trying to explore some of these applications in the next few years. For wearable electronics, again, there is something very interesting, not only phosphorus quantum dot, several such 2D quantum dots can be connected together by organic linkers. You can make wearables, structurable power sources, and embedded sensors in one structure, integrated structure for flexible electronics. We hope we should be able to continue from Mr. Tirupati some of this work. I spoke about these materials, however, the phosphorus quantum dot was done by one of my PhD students at Central Electrochemical Research Institute, Dr. Manila, who is a postdoc now in Canada. And we have some collaborations. Dr. Subhaya Alvarepan from Central Electrochemical Research Institute was involved in making phosphorus quantum dot. And Shailaja Krishnamurthy from National Chemical Laboratory did the DFT calculations for our phosphorus quantum dot. And I have a collaboration with Rice University with the Professor Pulikalajian, who does a lot of other 2D materials. The photoluminescence studies as well as the time resolved measurements were done by Professor Amitabh Patra from IACS along with one of his students, and many other students like Dr. Sumana Kundu, Dr. Jason, and Dr. Minnaya. They were involved in other 2D materials which I did not talk today. With this, let me thank all of you for your patience, and I will be happy to answer any questions to phosphorus quantum dot. Thank you all.
Thank you so much, sir, for giving an exciting lecture on phosphorus quantum dots and its potential applications. So I'll be happy to take your 1 or 2 questions since it is the last speaker.
Sure.
Sorry, I should be not be biased, but yeah.
Shall I stop so that I can see the chat box if there are questions?
Yeah, I think since we are not taking any questions, so that's why maybe it's not there in the chat box. But I'll request all the participants, if you have any questions, please ask
Please.
1 or 2 questions.
Please.
Sorry, actually, to all the other speakers that we could not take the questions. So I apologize for that.
Yeah, that's okay. That's all right. Yeah.
But some of the speakers are available, right? We can continue.
Yeah.
Okay.
So I'll be
okay, please go ahead.
So please ask questions if you have anything.
I see something in chat box. No.
No questions.
No question. Don't worry. Yeah, that was excellent
But they can
lecture.
ask.
Yeah. They can always ask. They can also contact you as well. Okay.
Sure.
Yeah. Yeah. Dr. Rai, can I take 1 minute?
Yeah, please, sir, please.
Yeah. So we have now completed 5 lectures. Really excellent. We have gone through a variety of subjects across the chemistry. We had organic chemistry, we had materials, we had theory, we had chemistry at biology interface, we have again materials at energies, and so quite a variety of lectures are there. I thank each and every speaker, Dr. Basavaya, Dr. Rangarao, Dr. Mangal Sundar, Dr. Mukesh, Dr. Vijay Mohan Pillai. All these I immensely thank them for sparing their valuable time in this particular symposium, and helping all of us, including a lot of youngsters, to learn, look at various things that are going in chemical sciences, and which they can pick up as the future research problems, etc. So I think with that, perhaps we can close this technical session 1, and probably we can move into the technical session 2, which is the flash presentations. So a request to all the flash presentation speakers is that the slides will be controlled by our colleagues here. So you please don't share the screen. The screen will be shared here. Okay, and kindly restrict to the time. And my request is all of you who are presenting today, please do log in tomorrow also by 9:15. And so we can only issue these certificates for those who have completely attended these sessions. Okay, so that's what one of the things that the committee has planned. Kindly, all the speakers, the flash presentation speakers today also do log in tomorrow, and our session will be at 9:15. Kindly try to log in tomorrow by 9:15, all of them. And now this particular session will be taken over by Dr. Rajiv Biswas. So Rajiv, go ahead and start the session.
Yes, sir.
Unless you wanted some few minutes break.
No, I think we are okay, sir. If
Okay. Okay.
so, yeah.
Yeah. Okay.
Thank you, sir.
Thanks a lot. Yeah. Thank you.
Yeah. So as Sir has explained, so this each flash presentation will take will be of 4 minutes duration. So I will change the slides, and we are keeping track of the timing as well. So until and unless you are facing any technical issues, we will move to the next speaker when the 4 minutes is over. And yeah, I did not see Miss Pooja for this presentation throughout the session. If you are there, so please be ready. I did not see you. Okay. So our first speaker is Professor Vijay Raghavan from Vellore Institute of Technology. And he will be giving us the first class interest. So Professor Raghavan.
Yeah, good evening. Thanks to the HOD, chair and organizer. It is my pleasure. Am I audible, Dr. Biswas?
Yes, sir.
Yeah.
Thank you very much. Let me give some executive summary of the work before I present the slides. The motivation is to design and synthesize a catalyst that generates reactive oxygen species in presence and absence of light. Okay. So far, the reactive oxygen species are generated by presence of light only. So we have made the nanocomposite of zinc peroxide and polypyrrole that generates reactive oxygen species like H2O2, superoxide, OH radical in absence of light too. The significance of this work is if you employ this catalyst for water recovery in effluents, say dye, it can work 24/7. So the commercially available TiO2 catalysts require UV light activation, so it is not completely useful in the absence of light. So we have made this zinc peroxide polypyrrole catalyst, and we have published this in scientific reports and Journal of Physical Chemistry. We just got the patent granted, Indian patent granted 2 days back. So this is the behind the overview of the work. Let me explain the results. So as you can see, the first slide, the results show the degradation of the rhodamine B, a toxic dye, which is present above Q limit in the effluent even after treatment. So okay, so 10 ppm concentration we have taken. What is plotted is wavelength and absorbance. As you can see on the right hand side, zinc peroxide polypyrrole composite. Starting from 0, you have the absorption maximum here, and then it comes down. Then if 10 minutes is come down, 20 minutes is completely degrading. The polypyrrole alone cannot degrade. Similarly, zinc peroxide alone cannot degrade in absence of light. That is dark I have given. So the synergy between zinc peroxide and polypyrrole, that's the magic that creates reactive species that we have estimated. I have not shown that. Okay, next slide, please. Now the summary of the products that our catalyst with the commercial catalyst I have shown. The first one is our catalyst. You can see that 10 ppm dye, it degrades 100% in the dark. So when not dye concentration 23 ppm, it degrades 81%, then 96%, then 100%. The rate constants are given here. Accordingly, go to the diffuser catalyst here. Rhodamine B, the same 10 catalyst 10 ppm concentration we have taken. The catalyst amount is the same millimole we have standardized. No action in the dark, no action in the visible, only the UV light is being used. This is the catalyst being used currently, diffuser catalyst in commercial catalyst. Okay. So these are some of the other catalysts with the polypyrrole, with the TiO2 that doesn't degrade in the dark because they cannot generate H2O2. I will show the mechanism in the next slide. The rate constants are also very high. The mechanism in the dark is chemical, not photochemical. The chloride ions generates free radical, free electrons on the polypyrrole system. These free radicals are consumed by H2O2. This H2O2 is generated by the zinc peroxide when you suspend in water. Obviously, we are doing the reaction in aqueous medium. This is in equilibrium. This H2 is a ppm level, you estimated. This H2O2 scatters this electron, thereby generating all the OH radical, usual mechanism. So in the dark, we are having the chemical mechanism, chemical way of producing reactive oxygen species that degrades the dye, which has not happened so far. Reactive oxygen species is the best way to degrade dye. It's called advanced oxidation process, not absorption process. Okay. Next slide, please. So we have shown that here the activates the visible light. In the visible light, the polypyrrole has got a band gap of 1.2 eV. Obviously, it absorbs excitation across the band gap. You have the photocatalytic mechanism usually operating. All the reactive oxygen species are generated. Next slide, please. So here the UV light, the band gap of zinc peroxide is 3.2 eV. It absorbs the UV region, then reactive oxygen species are generated across the holes and electrons are generated, and there those oxidation reaction reactions. Essentially, by combination of zinc peroxide and polyphenol, we have generated reaction species in the dark, which is not known, and in the UV light and visible light in a nano composite. So we can, since it's a polymer, we can always dope, and applications could be a lot. Okay. Next slide, please. So I thank, in fact, this is from the Oxford Inorganic Chemistry Lab, which is a historic building where John B. Goodenough discovered lithium battery, and I visited 5 years back, and proud to be there. I was visited, and again, I must thank here my graduate student, Lakshmi Prasanna, who is doing postdoc now in Tel Aviv University and in the Center for Water Technology. Thank you.
Thank you, Professor. So you are rightly on time. So our next class presentation is from Yunus Ali. So Yunus, please go ahead.
Am I audible, sir?
Yes, please go ahead.
Hello everyone, good evening. I am Sir Yunus Ali and will present our recent development on stochastic resetting to prevent the abnormal precipitation accumulation caused by global warming. Next slide, please. Next. So we all aware of the fact of the global warming and its effects. Global warming is the continuing slow increase the average temperature of the Earth's surface. According to the National Oceanic Atmospheric Administration, the average global temperature has increased 1.4 degrees Fahrenheit over the past 100 years. The effect of global warming on our planet and the climate system is very destructive, like in rising sea level, abnormal drop, flood, melting in ice, etc. In this project, we address the change of precipitation accumulation at an increased temperature. Essential development and the below picture development by Neely and his group predicts that in the century, 3 degrees centigrade global average warming will really regionalize the probability of abnormal large accumulation in the order of 100 that have historical precedence. That means number of heavy flood on our planet would increase 100 times than the normal one. Next slide, please. So we address this situation using stochastic climate model for the climate system and try to find some possible solution to the problem using concept of an stochastic setting to moisture content of the atmosphere. The climate system follows the time evolution equation expressed in a first equation. This is where x is the column indicator water moisture, b is the precipitation rate, and c is the stochastic convergence rate of the moisture, which is termed as noise. One can understand the phenomena using schematic diagram. So in this schematic diagram, we can see when water moisture crosses a lower threshold x0, the precipitation started, and the event terminated when the water moisture comes to xa. Precipitation rate always tries to reduce the amount of water moisture, and convergence rate of moisture tries make it stochastic. For the present purpose, we define two variables, S and S bar. S represents time integrated accumulation in a single rainfall event from the beginning of the precipitation event. So the equation you can in the slide. And S bar represents the amount of water rained up to a time t within event. From the climate equation, we construct Langevin equation of motion. After that, from Langevin equation of motion, we derive the associated Fokker-Plane equation of motion for our problem. Next slide, please. So by solving Fokker-Plane equation, we get Q of S, which is the probability of an S amount of water rained out within an event. We solve Langevin equation numerically improved by Euler method. In this figure, the left side figure, points are representing the numerical simulation result and lines are representing the analytical result. We see P of S increases drastically by the increased moisture convergence strain for a heavy rainfall event, and this is the order of 100. To deal with this situation, we implement a permanent cutoff of the column in the water moisture. We say the condition that the amount of water moisture cannot cross the cutoff value XR. We observe that integrated water moisture at the optimum restart rate upper cutoff decreases the precipitation accumulation possibility. So therefore, the implementation of optimum upper threshold value on the column integrated water moisture content can efficiently reduce the P of S for heavy rainfall event. Next slide, please. Next slide, please. However, to implement this is energetically costly and technologically challenging. So we implement stochastic restricted restart. This diagram shows the mechanism of stochastic restricted restart. We will check after S gap where the moisture exists. If it crosses the XR value, then we restart it from XR. Otherwise, doing nothing. We implement this condition setting and we got the following result. So the result in the below picture, this is our result. We see that optimum restart rate X R equal to 5. The precipitation accumulation associated with the above current climate cutoff scale decreases to the precipitation accumulation at the current climate cutoff scale for the large accumulation site. Next slide, please. Next slide. So now the question how to decide the optimum restart rate is 5. Now plotted P rest and P rate versus R. Where P rate is the probability of precipitation accumulation with an upper cutoff in the amount of column indicated water moisture, and P rest is the probability of precipitation accumulation with a conditional resetting. We see that R is almost 1. Therefore, we can conclude instead of setting a permanent threshold of a column indicated water moisture content of the atmosphere, one can reduce heavy precipitation accumulation using a stochastic resetting technique. So now go to next slide. Please, next slide, go please. Next slide, sir. So this is I acknowledge the following people: my labman Navadip Chaudhary and my supervisor Dr. Devashish Mandan, my institution I Tripati, and my labmates and following institution. Thank you for listening.
Yeah, thank you, Yunus. Our next presenter is Dr. L. Subramanian Sharma. So please go ahead, Dr. Sharma. Dr. Sharma. Please go ahead.
Yeah, Dr. Sharma is there.
Unmute yourself. You have to unmute.
Dr. Sharma, you have to unmute, please.
Okay.
Dr. Sharma. Dr. Sharma.
So we will get back to you again. So let us move to another presentation. Presentation by Sanchayita De.
Am I audible?
Yes, you are audible. Please start.
Okay. Good evening, everyone. I am going to present the topic entitled as Metal Ligand Cooperativity Driven Non-Spectator Feature of Benzofuroxane and Benzodifuroxane. Metal ligand cooperativity implies participation of both metal and ligand during the bond activation process where the chemical environment around the metal and ligand have been changed. Now I'll introduce the ligand benzofuroxane. It is a biologically active nitroso donor and a ring-chain tautomeric form of 1,2-dinitrosobenzene. Now, benzofuroxane on its symmetrical cleavage can bind to a metal via its neutral mononegative or dinegative oxidation states, and the oxidation state of the ligand in a metal-ligand complex can be confirmed from the NO bond distances of these complexes. The extended ring fission of benzofuroxane led to its symmetrical cleavage, which was first reported by Hawk. Next slide, please. The symmetrically cleaved NO-NO complexes of benzofuroxane were reported with moderate to strong pi acceptor ruthenium bipi2 and ruthenium pap2 precursors. However, an unsymmetrically cleaved kappa2 NO binded complex 2 was produced in conjunction with electron deficient ruthenium hydride precursor via the formation of a hydrogen bonded kappa1 coordinated intermediate 1. The theoretical investigation showed that the unsymmetrical cleavage of benzofuroxane is energetically more favorable than the symmetrical one. On the other hand, an unprecedented solvent incorporated NC coupled dimeric complex 4 along with a nitrosoanidido binded monomeric complex 3 were generated in a cascade reaction of electron rich ruthenium ACAC2 and benzofuroxane in ethanolic medium. Next slide, please. In the pretext of the non-spectator feature of benzofuroxane, the reactivity scenario of its extended family member 4,5-furoxane benzofuroxane or benzodifuroxane has been recently explored. It is a ring-chain tautomeric form of 1,2,3,4 tetranitrosobenzene and a better nitroso donor than benzofuroxane. Now, this benzodiafuroxane on reaction with electron-deficient ruthenium hydrate precursor displayed a variety of coordination modes, including kappa-2NO, kappa-2NN prime, mu bis kappa-2NO, and kappa-2NN double prime. And the symmetrical cleavages of benzodiafuroxane is still yet not explored. The ring fission of 14 pi electron aromatic benzodiafuroxane in its free state is not possible, but it can be achieved by the cooperative interaction of metal hydride and amphiphilic benzodiafuroxane. Next slide, please. Attack at different nitrogen centers, that is N3 or N6 positions of benzodiafuroxane, led to the formation of differently coordinating intermediates like I1 and I2, which can then be transformed to the complexes 5 to 8. A rarely manifested kappa-2NN double prime binding mode in complex 10 can be produced from the intermediate I1. The dimeric complex 9 can be formed by the hydride attack followed by simultaneous coordination of benzodiafuroxane to the metal centers. Next slide, please. In conclusion, we can say that the cooperative interplay between the metal hydride and benzofuroxane or benzodiafuroxane facilitated the aromatic ring fission of this kind of ligands. The electronic modulation at the metal fragments explore variety of binding features of these kinds of ligands, and the redox non-innocent features in the functionalized ligand in the metal complexes have been observed. The coordination flexibility led to diverse chelating modes of benzofuroxane and benzodiafuroxane. Thank you all for listening.
Thank you. Yeah. So one of the participants, J. Lakshmi Devi, can you please put your audio off? Can you please put your audio off? Audio mute mode. Audio and video also, if possible. Yeah, those those who are presenting the flash presentations, I request, if possible, you can turn on your video also, because it is getting recorded. That will look good. So our next presenter is Dr. Saripalli Sudhakar Reddy. So Dr. Reddy, please go ahead.
Can you hear me?
Yes.
Okay, Biswas, thank you very much. Okay, I would like to talk about Lewis acid-base adduct type organic whole transporting material that has been applied for perovskite solar cells. Can you please move on to next slide? So before going to this, I would like to give brief explanation about a perovskite solar cells and what is the working principle, how does it work. Here we can see that energy level diagram. Actually, perovskite material will absorb the sunlight, and then there is like exciton formation like holes and electron that will be transferred towards the respective electrodes, that is like anode and cathode. That interfacial materials, especially ETM and HTM, actually plays a significant role in perovskite solar cells by enhancing PCE and also stability. The PCE is calculated by using JSC, VOC, and fill factor. And more importantly, PCE is very important, and more importantly, that VOC, fill factor, and JSC is very important. And especially FF is mainly depends upon the charge transport, and the VOC depends upon the home and lume of the materials. And overall, the JSC that mainly depends upon the overall absorption spectra. So can you please move on to next slide? So perovskites, like perovskite is like A, B, X, 3 type, where A and B are the cations, and A is a methyl ammonium cation, and also like ethyl ammonium cation, whereas B is like germanium, tin, lead, such kind of cations, and X is like a halides. That again, AB, that perovskite materials is classified into two types. One is like a mesoscopic, and also another one is a perovskite solar cells. In this mesoscopic, actually mesoporous TiO2 has been used in this device structure. Okay, coming to planar perovskite solar cells, there are two types. Okay, in that again, one is the NIP planar structure, and also one more is PIN. Everything this device structure is mainly depends upon the how that electron transporting material and that anode and cathode has been arranged. Okay, regardless of the device structure, interfacial engineering is very important, especially whole transporting material. Whole transporting material plays a significant role in this perovskite solar cells. Can you please move on to next slide? These HTMs again classified into two types. One is organic HTM and also inorganic HTM. This organic HTMs again classified into three types. Among them, small molecular HTM plays a very significant role in perovskite solar cells. Among these materials, Spiro OMT is one of the best material as of now. Indeed, it's commercially available material, and also PTE is one more material, and Actually, an ideal HTM consists of like a compatible home energies, and also it should have very good solubility, and also it should have very high hole mobility and also conductivity, and the material should have high thermal mobility. Although Spiro OMET is having high efficiency, by using additives and dopants of TBP and also lithium TFIs, that stability has been decreased dramatically. Therefore, I designed a new material. Can you please move on to next slide? I designed a new material by incorporating pyridine material by extended conjugation with benzene thiophenol and also 10 mol groups with triphenylamine. This is a new design we incorporated in this pyridine material to enhance the stability as well as a power conversion efficiency. So we did all the characterization for this materials, and this material is showing that high absorption coefficient. And we also examined cyclic voltammetry in order to find out the home energies of this material. We found that minus 5.06 electron volts, which is suitable for the perovskite material, which is like adjacent material. And also this material is showing high glass transition temperature of 120 degrees centigrade as revealed by its DSC. DSC means differential scanning calorimetry. We also investigated the PL quenching in order to know that how electron transfer is effectively working in this material. And it's showing that P by THTP that has been synthesized by me, along with that BCF material we doped in that one. After that, it quenched very effectively when compared to that of when compared to that of pure HTM and also perovskite material. In addition to that, we also measure TRPL, that means transient PL. Among them, when we added a BCF and also HTM, it shows that 1.79 nanoseconds. That means that this HTM is very efficiently working. It's very fast excitation, and also it can extract holes from the photo generated perovskite material, and it can transfer to the respective electrode. And also when we fabricate a device like that is perovskite solar cells, you can see the left side complete corner one JSC. You can see that there is no hysteresis effect. That means that reverse and bias, like the one is a reverse, one is a forward. Inside you can see that legend one. There is no negligible, completely negligible hysteresis. That is one of the significant factor. And also we got the average BCF 16.57% for the when we doped PCP, when we doped BCF into the HTM material. And also Spiro OMET is the commercially available material. It's kind of a reference material. It was like only 12.36%. The one more the significant factor in perovskite solar cells is the stability one. We got like a very good stability up to 30 days one, like approximately 720 hours. We got very good stability when compared to that of commercially available Spiro material. In order to understand why the stability is very high, we also examined that actually water contact angle. When we measured water contact angle, we measured for all three samples, like our HTM plus BCF and also Spiro OMET plus BCM and also pure HTM material. So among them, our material with BCF has shown 82.2 degree, which is like hydrophobic in nature. That was one of the reasons to enhance the stability of our perovskite solar cell device by using our material. Can you please move on to next slide? We also examined TFT, thin film transistor, in order to understand that the material having high mobility and conductivity. So this, as depicted in the figure, this TFT results demonstrated that the conductivity of this material has been dramatically increased. So overall, I would like to conclude that our material interacted with the BCF, and this actually interacted with the perovskite material in the device structure, which will be more beneficial for the selective of holes. Thereby, efficiency will be increased by extracting the force from the perovskite material, and it can easily transfer to the respective electrode. That was the reason. And more importantly, we got very smooth surface morphology by using SEM and also AFM. The main reason, we also proposed a mechanism. What would be the reason for enhanced efficiency as well as stability? This was LABA, that means Lewis acid base direct formation of this material. That means that pyridine material and also BCF is a dopant we use in this material. This was interacted, and this was interacted with our perovskite material. That is like a methyl ammonium leaded material. So this is like new proposal. We proposed this one, and move on to next slide. Thank you very much. Especially I need to thank especially IIT team. Thank you very much.
Yeah, thank you. So next is Srilata Polepalli from IIT Bombay. Srilata, please go ahead.
Am I audible, sir?
Yes.
Hello, good evening to everyone. I am Srilata Polepalli from Department of Chemistry, IIT Bombay. And today I would like to give a brief overview of one of the work, copper phosphate moringa oleifera coagulant protein hybrid nanoflask for selective detection and removal of toxic inorganic metal ions and organic dyes from water. Next slide, please. Many of us know that drumstick is normally commonly used vegetable in our diet. It has many properties. It's known as superfood, medicinal use, biofuels, and it is also used in textile industry. But one of the important and interesting property is its water coagulation ability. So we wanted to explore this property. So we have used a drumstick seed powder for dye absorption and heavy metal ion absorption studies. We can see from these bar diagrams and the photographs that anionic dyes are absorbed to greater extent by the drumstick seed powder, and also heavy metal ions are absorbed lead, cadmium, mercury to greater extent. So we wanted to know what could be the reason behind this. So we have purified a small molecular weight protein from drumstick seeds that is called as Moringa oleifera coagulant protein. It is approximately 13 kilodalton in molecular weight. We can see from the SDS page and MALDI. And the CD spectra shows that it's mostly alpha helical type of protein. Interesting aspect of this small molecular weight protein is it is a cationic charge protein from the more amount of arginine and histidine residues that are present from the amino acid sequence, which you can see over there. Next slide, please. So using this protein, we have synthesized copper phosphate nanoflowers using this relatively simple co-precipitation method. And we have used different concentration of MOCP proteins to see different kind of nanoflower structures. And relatively at 0.1 millimolar concentration, we see a very nice floral kind of morphology at nano level. With increasing protein concentration, we are able to observe that the petal density increases and the nanoflower size decreases. Several other characterizations were also performed using powder XRD and FTIR, where the inorganic component was found to be copper phosphate and the protein presence was found by the amide bonds from the FTIR. Also, we have seen that it is a cationic charged protein. So using the zeta potential analysis, we were able to show that the protein, with increasing protein concentration, the surface charge zeta potential cationic charge increases in these nanoflowers. Also, these nanoflowers were found to be highly stable from the TGA analysis. Next slide, please. So firstly, we have done dye absorption and heavy metal and dye absorption studies and degradation studies using these nanoflowers. So from the photographs and also the graphs, we were able to, we can see that the anionic dye absorption is much more greater compared to the cationic dyes because the protein which is used in these nanoflowers is cationic in nature. Also, the dye degradation studies were performed in the presence of H2O2. And from the SEM, we can see that even after 10 cycles, relatively the nanoflower structure remains intact, which is very useful. We can even go to higher cycles. The dye degradation was due to the Fenton type of reaction mechanism, which showed using the 2-hydroxyterephthalic acid fluorescence at 430 nanometers. Next slide, please. Heavy metal ion absorption studies were performed using ICP-AES. So you can see from the graph that there is greater than 98% of absorption of lead-2+ as compared to mercury and cadmium. Even at relatively low concentration of protein of 25 micromolar, we were able to see that the lead-2+ absorption is as high as 95%. Different water samples were also utilized for to show how well the lead-2+ can be absorbed from them using these nanoflowers, Also from the SEM, you can see that the lead-2+ that is absorbed at the edges of these petals clearly in the form of needles, and which was also confirmed using the elemental mapping. Powder XRD XPS further also supports the lead-2+ absorption by these copper phosphate nanoflowers. Next slide, please. So in conclusion, we were able to synthesize a new nanomaterial called copper phosphate nanoflowers using a naturally available protein MOCP, and we have used these to demonstrate dye absorption, dye degradation, and heavy metal ion absorption. So thank you one and all for, I would like to thank my supervisor, IIT Bombay and DST Inspire, and also the National Symposium conducted now and IIT Tirupati for giving me this opportunity. Thank you.
Thank you, Srilata. So next speaker is Raka Hamed from IIT Tirupati. Raka, please go ahead.
Good evening, everyone. I'm Raka Ahmed from IIT Tirupati, and in this presentation, I am going to talk about how one can tune photoinduced charge transfer in non-covalently bound zinc porphyrin and carbon fullerene-based donor acceptor complex. Next slide, please. Zinc porphyrin PCBM complex is well known, experimentally synthesized, and has huge importance as an organic photovoltaic material as it shows interfacial charge transfer state which facilitates the electron hole charge separation. As we all know, organic material have large exciton binding energy. These charge transfer state plays the most important role in the charge separation process. Here, our interest is to tune this charge transfer state and accordingly the charge transfer efficiency without affecting its structural stability. For this, we have part out the donor molecule by selectively hydrogenating the pyrrole ring. The position of the hydrogenation is shown here. With one ring hydrogenation, we will get zinc chlorine, and with two opposite ring hydrogenation, we will get zinc bacteriochlorine. And these are all experimentally realized chromophores, which are mainly used in photodynamic therapy. Now, our object is to see when these two, previous slide. Our objective is to see when these two donor molecules will form complex with the same acceptor PCBM, what will be its impact on the structural stability, the charge transfer state energies, and the charge transfer efficiency. For this, we have implemented dispersion corrected DFT and optimally tuned RSH functional for TD-DFT calculation. Next slide. Next slide. Coming to the structural parameters, ascending distance decrease increasing hydrogen. The effectors can be synergetics weakly inhibiting, and the binding energies are mainly governed by the non-covalent interactions. So all these complexes are stable. Next slide. Next slide. Here, electron hole charge separated state is shown. With increasing degree of hydrogenation, the pi electron delocalization gets affected. And as a result, the donor localized HOMO level getting destabilized, whereas the acceptor localized LUMO is intact. So the HOMO-LUMO gap is getting reduced. And as a consequence, the charge transfer energy also getting decreased. Next slide. Coming to the photoinduced charge transfer efficiency, the charge transfer rates are calculated with the semi-classical Marcus theory. All the governing parameters are shown in this schematic diagram like reorganization energy, driving force in DMF solvent, activation energy. And the rate of zinc porphyrin PCBM is in agreement with previous experimental measurement. And the low-lying solvated charge transfer state explains the experimentally observed fluorescence quenching. And most importantly, the zinc chlorine PCBM shows the highest rate among all the three complexes. Next slide, please. Now, I would like to conclude by saying all the DA complexes are stable. With selective pyrrole ring hydrogenation, one can tune the charge transfer state energy and the charge transfer efficiency. And among all the three DA complexes, zinc chlorine PCBM is the best performer. For more detailed discussion, you can check our article in Physical Chemistry Chemical Physics Journal. And in the end, I would like to acknowledge my advisor, Dr. Arun K. Manna, for guiding me to do this project, and IIT Tirupati. And I would like to thank the organizers for giving me the opportunity to present here. And thank you all for listening.
Thanks, Radha. You are right on 4 minutes. Next speaker is Dr. Srinu Totari. So,
Yes.
Dr. Srinu, please go ahead.
Yes, thank you. Good evening, everyone. Today, I'm going to talk to you about morphological evolution of two-dimensional porous hexagonal trimesic acid framework. Next slide, please. In everyday life, we are come across different crystalline materials like salt, sugar, diamond, and copper. So if you see these crystalline materials, they have a different ions, molecules, atom in their crystalline lattice. So if you understand those crystalline, if you understand these materials appropriately, we can use and in various applications. Today, I'm focused on molecular crystals, where molecules are interacted by hydrogen bond or weak intermolecular interactions. Next slide, please. Coming next, here I'm going to talk to you about a trimesic acid, where the carboxylic acid are interacted via acid-acid dimer, and it can extend to form a hexagon. It still further extend to form a two-dimensional hexagon. So, but if you see the form 1, it has a interlocked structure, and next please. And if you see the crystal structure of a trimesic acid, it is a triply interlocked, a closed packing. So what the problem? The problem is about 50 years back, the single crystal structure of trimesic acid was known, but it has about 1600 structures are there in the CSD, which either exist in a co-crystals, salts or solvates or hydrates. In all the crystal structures, it's existed as a form 1, means we are seeing the interlocked structure. But so far, no one has isolated the pi-pi stacking structure. Next, please. Yeah. So if you see the form 2, next, form 2 structure, you see here, you can see if you tilted 90 degrees of this form 2, you can see the pi-pi stacking, which is the distance is about 3.3 angstrom, which is also mimics the graphite. You can see it mimics the graphite. Next, please. Yeah. Next slide, please. And we also studied the morphological evolution of this trimesic acid form 2, and we have taken form 1, which has a block shape. With time, it is going like a fiber-like morphology. Next, it forms like a self-assembly morphology, and afterwards, it forms like a hexagonal solid rod, and afterwards, it forms like a hexagonal halo rod, and eventually, it is going back to its initial state. Next slide, please. As I said, the crystalline material of form 2 has some porous in nature. So we also studied rhodamin B, which is a pollutant in the textile industry, and we try to see whether it can be absorbed by form 2 and form 1. Form 2 shows a more absorption because of its porosity and compared to the form 1. The form 2 is almost about 80%, double of the form 1, absorption is there. And next slide, please. And if you see the single crystal structure of form 2, it has a hexagonal single crystal structure, hexagonal in nature. If you see the morphology, that is also in hexagon. And if you compare the nature's honeycomb, it is also an hexagon. So we are mimicking the crystals with the nature. So it is the smallest honeycomb in the crystal structure. It is the smallest honeycomb structure of the molecules. And next, so if you see as it forms a two-dimensional hexagonal sheet, so now we are working, can we take out the single layer of this two-dimensional form 2 trimesic acid? So later we are also working on, does it behave like a graphene, or we are working on this project currently. And I would like to thank DST SCRB, and also I would like to thank CSIR and NCR. I also would like to thank IIT Tirupati. Thank you so much. Thanks for your kind attention.
Thank you, Dr. Sinu. Our next speaker is Mr. Syed Akhil from SRM University. So,
yes,
Akhil.
Yes, sir. Good evening, one and all. I thank the IIT Tirupati Organizing Committee for giving this opportunity. I, Syed Akhil from Department of Chemistry, SRM University, AP. Today, I'm going to discuss my recent work, completely amine-free open atmosphere synthesis of high-quality cesium-lead perovskite nanocrystal. Next slide, sir. And perovskites are the structures which are having with ABX3 structures. These are in inorganic and organic and inorganic hybrid structures, which is known cesium-lead halide perovskite nanocrystals, which are known for more than 50 years. So next, sir. More than 50 years. These were first colloidally synthesized by Professor Cole and Co. in the year 2015 by hot injection method. They have used oleic acid and oleolamine as surface capping ligands, and they have changed spectra from spectra from 400 to 700 with a wide tunability, and by varying their halide composition, they have broad absorption and very narrow emission, which are useful for these solar cells and light emitting diodes and lasers. So these are having with photoluminescence with 98%, and currently there are challenges coming due to the stability effect. These are having oleolamine as a surface capping agent, which is taking halides from the crystal structure and making defects on the structure, which destabilizing the crystal structure and decreasing the photoluminescence quantum yield. So here the amine is a problem. So next, sir. So currently the other alternative researchers synthesis are going by other researchers are trying to work on this. So they are using trioctyl ammonium halide, which they are using amine in this synthesis. But in our case, we want to use a completely amine-free synthesis by three precursor route. Like we have first synthesized with a hydrobromic acid, which is a facile bromine source, and trioctyl phosphine as surface capping agent, and oleic acid as surface capping agent in completely open atmospheric condition. And then we have got the cesium-led bromide perovskite nanocrystal, and this is a TEM image. So shown, this is a TEM image. So next slide, please, sir. And we have studied the systematic study of amine-free cesium-led bromide with the variation of bromine precursor and variation of TOP surface capping ligand, and we have optimized the various concentrations of bromine and TOP, and we have got the very high photoluminescence sample, which is we have seen here in FTR spectra. There is a we can see this prominent peak at 1140, which is representing the TOP as surface functioning group, and we have next, sir, next. And this is we have tuned the spectra from 400 to 600 by varying the halide composition, like anion. We have did the halide anion exchange, and then we have got this tunability spectra from violet to red. Next. And as I discussed before, these are having the photostability issue. So we have studied the stability of these both the colloidal solution and thin films. We had it with 0 days to after aging for 90 days. We have got this. There is nothing change in this optical spectra in absorption or photoluminescence or in change in the XRD patterns. Or we can see these clear pictures which are having showing these digital pictures which have taken in under UV edition. And so next. And we have got the photoluminescence of 70%. And we have also did photoluminescence quantum yield percentage was a number of days, and we have said this is more than stable for 3 months. We can see this in the figure. We can see this these are very high stable for more than 90 days without any consistent in the with the respect to days when compared to the normal convention method. And we have did the next slide. And we have finally I can conclude that we have got this completely amine-free open atmospheric condition by three precursor approach, and we have got in open atmospheric condition with the photoluminescence quantum yield of 70%, and it is more than stable for 3 months, and it is having this high quality cesium-led bromide crystal can be used for LED devices, light emitting devices, and this is just accepted in Chemistry European Journal. And this, if you are interested, you can please check it. And I finally acknowledge SRM University AP and my Dr. Nimay Mishra sir and my co-author. And thank you for IIT Tirupati for giving this valuable. And thank you for all for your time. Thank you so much.
Thank you, Akhil. So our next presenter is Ms. Pooja Prashantan from IIT Bombay. Pooja, please go ahead.
Okay. Myself Pooja Prashantan. I'm working under Professor Nandakishore, Department of Chemistry, IIT Bombay. So today I'm presenting inhibition of aggregation by two non-steroid anti-inflammatory drugs, ketoprofen and phenoprofen, biophysical insights. Next slide. So as we all know, protein misfolding and aggregation are major characteristics of many neurodegenerative diseases, such as Alzheimer's, Parkinson's, prion disease, etc. Various strategies has been adopted to combat with diseases. Inhibition of aggregation by various materials, various small molecules, nanoparticle, polyphenols is extensively studied, but the inhibition mechanism is not very well explored. So more insights, a deeper understanding of mechanism of inhibition can provide new strategies to combat with these diseases. In the current study, we have chosen two non-steroid anti-inflammatory drug, ketoprofen and phenoprofen, and we have studied their effect on aggregation of human serum albumin. Human serum albumin is a major transport protein in the body. Next slide. So first we have studied the binding interaction between these drugs and E2HSA. Binding studies has been characterized, we have studied by isothermal titration studies and docking studies. ITC studies suggest that both these drugs show similar affinity with both the drugs. Both ketoprofen and phenoprofen show a moderate affinity of the order of 10 to the power 4. And negative enthalpy change is associated such as that electrostatic interaction is the predominant force between these drugs and HSA. And we also shown temperature dependent study, and there's no much temperature significance. And we have carried out molecular docking study. HSA has two major drug binding sites, and docking study suggests that both ketoprophene and phenoprophene binds to site 1 of HSA. Next slide. Then we have studied the fibrillation of HSA at pH 7, and we have incubated the HSA sample at 65 degrees for 24 hours. The kinetics of HSA fibrillation has been studied by THT binding assay. THT is a well-known marker for amyloid fibrils. It selectively binds to fibrils and show fluorescence intensity at 450 nanometer, once excited at 450 nanometer. And we have, as we can see from the plot, both ketoprophene and phenoprophene inhibit the aggregation in a concentration-dependent manner. Ketoprophene at concentration greater than 1 millimolar and phenoprophene at 0.5 millimolar can completely inhibit the fibril formation, which indicate that phenoprophene is a much better inhibitor compared to ketoprophene. And we have also carried out dynamic light scattering and CD studies. Circular dichroism studies give the confirmation of the protein at different stages of aggregation. As we can see, the concentration at which complete inhibition is observed, there is no change in the spectra even after 24 hours of incubation. It is not converting into beta sheet structure. DLS studies also, at a higher concentration, no significant size change of the protein even after incubation. Whereas for native protein, we can see as we increases the time along fibril phase has a much lengthier, it showed 36 nanometer, around 36 nanometer length, which again indicate that phenoprophene observed to be a much efficient inhibitor compared to same concentration of ketoprophene. Next slide. Then we have used differential scanning calorimetry to study the fibrillation, to get more insight to the fibrillation. We have recorded the thermal behavior of the protein at different stages, that is native state, that at which the no incubation and that elongation phase and the maturation phase of fibrillation. And as we can see, we have recorded the thermal behavior of the protein at different stages in presence of different concentration of these drugs. These two are the spectra corresponds to complete inhibition, the concentration at which complete inhibition is observed. As we can see, a greater extent of stability of the protein in the presence of both these drugs, and extent of stabilization is higher in the presence of phenoprophene. And also, at a higher concentration, even after 24 hours of incubation, the protein remains unchanged. The thermal behavior, that means the stability is unchanged, which indicate that protein can exist in a native form even after 24 hours of incubation at 65 degrees Celsius. Then we have also carried out isothermal titration calorimetry. We have taken samples at different stages of incubation and studied their binding with the drugs. And these studies suggest that the electrostatic interaction is a major force because this protein is interacting with the fibrils mainly by polar interaction, and the extent of polar interaction is higher in the presence of at native state, which indicate that the protein interact with the drug at native state, which prevent further fibrillation. Next slide. In conclusion, the major conclusion we drawn from this study are both ketoprophene and phenoprophene show a similar affinity toward HSA, but their inhibitory action is not the same. And the mainly electrostatic interaction between these drugs and protein play an important role in inhibition of aggregation. So this understanding of structural property drug molecule can provide useful insight into development of new strategies in rational drug design. Next slide. So I would like to thank my supervisor, IIT Bombay, CSIR for providing financial support, and IIT Tirupati. Thank you.
Yeah, thank you. So our last
Audible, sir, now?
Yes, you are.
Oh, thank you so much. I'm sorry for the disturbance happened earlier. Today I'm going to give some information about graphene supported platinum copper bimetallic nanoparticles for improved oxygen reduction reaction for fuel cell application. Next slide. Yeah, actually, I thank the work which I'm going to present today is done by my student, Mrs. Shravani, who is a DST Inspire Senior Research Fellow working with me. Next slide, please. Yeah, this afternoon, Professor Ganesh sir, as well as Professor Rangarao and Professor Vijay Mohanan Pillai sir has emphasized the importance of hydrogen economy. Hydrogen can be used as a fuel in the energy conversion device like fuel cells. Actually, you can use any type of fuel beginning from hydrogen, methanol, ethanol, or formic acid in the proton exchange membrane fuel cell, but these all are anodic fuels. But at the cathode side, we have to focus more on the reduction of oxygen. So we are working to develop the nanoscopic electrocatalysts both for anodic oxidation as well as cathodic oxidation. And I'm going to show these platinum copper bimetallic nanoparticles deposited on reduced graphene oxide as well as titanium dioxide composite, because in the case of fuel cell reactions, the platinum based nanoparticles need to be dispersed on highly conductive carbon based supports, and that is the reason why we have chosen this graphene oxide as a support. Next slide, please. Yeah, actually, we started with the fabrication of graphene oxide by following modified Hammers method. By using the natural graphite and oxidizing agents. So we have prepared this graphene oxide, and later the titanium dioxide is prepared by using a solvothermal method where titanium isopropoxide and alcohol is mixed and exposed to heating, and then graphene oxide powder was mixed and for the preparation of this titanium dioxide and graphene oxide composite. Later, this composite is added to the starting materials of platinum 4+ and copper 2+ ion, and we used ethylene glycol, which act as both as a solvent as well as a reducing agent to reduce platinum 4+ as well as copper 2+ on the graphene oxide TiO2 composite. During this process, the ethylene glycol not only reduces platinum 4+ and copper 2+, it also reduces the graphene oxide to reduced graphene oxide. So the net result is we can get this bimetallic platinum copper nanoparticles on this reduced graphene oxide TiO2 composite. The particle size as well as the morphological observations we evaluated from the electron microscopy technique. As you can see, the high resolution TEM based on the d-spacings, we have found the platinum copper formation on the reduced graphene oxide TiO2 nanocomposite, and the particle size of this platinum copper is around 6 to 10 nanometer in size. Next slide, please. Yeah, so we have evaluated the electrochemical properties by making the slurry of this catalyst powder and deposited on the rotating disc electrode made with glassy carbon. And for the comparison purpose, we also evaluated the activity of commercial platinum as well as the homemade platinum deposited on reduced graphene oxide, as well as the platinum copper deposited on reduced graphene oxide. We have compared all these three catalysts with the catalyst what we have prepared. As you can see, we kept the platinum weight percent low when compared to the platinum weight percent of the commercial catalyst. Here we used 15 weight percent platinum and 5 weight percent copper on reduced graphene oxide TiO2 composite, whereas in the commercial catalyst the weight percentage of platinum is 28%. So the motivation of this study is to decrease the platinum loading for fuel cell reactions. So here you see the surface area what we have calculated for all these catalysts by integrating the area under hydrogen adsorption is about for the catalyst, the platinum copper deposited on RgO2 composite. The surface area is very high. It is about 67.35 meters square per gram, which is 1.5 times more than that of the platinum carbon, which is having the surface area of 42.89 meters square per gram. So this result shows that the oxygen adsorption and its corresponding reduction reaction activity will be high on this type of bimetallic platinum copper deposited on RgO2 composite. So this right panel shows that the diffusion limiting oxygen reduction reaction current density, which we have normalized to the glassy carbon surface geometric area, you can see that the catalyst platinum copper deposited on RgO2 is showing about 6.14 milliampere per cm square, which is almost 1.25 times more than that of the commercially available platinum carbon catalyst. So we also evaluated this diffusion limiting current density by rotating this electrode with different rotations per minute, and you can see the increased diffusion limiting current of the ORR. It shows that this is a diffusion controlled process. So as you can see, the net result is that by incorporating the copper to platinum and depositing on this type of composite. Next slide, please, sir. Next slide. So by depositing this platinum copper on this type of composite support actually gives the highest electrocatalytic activity towards the oxygen reduction reaction, which is for more importance and relevant for realizing the fuel cell efficiencies. And we proved that both the synergistic effect of participating platinum copper as well as this composite graphene oxide TiO2 support plays a crucial role in its improved performance towards oxygen reduction reaction. And this work we have recently published in synthetic metals which is having impact factor of about 3.3, sir. Thank you very much for your attention, and thank you very much for giving the opportunity to speak about our work in this important conference. Thank you so much, sir. Thank you.
Yeah, thank you, Professor Sharma. Thank you to all the speakers. Now I hand over the session to Professor Sipirao.
Concluding remarks.
Shall we allow for a few minutes any questions anybody has regarding posters, the flash presentations?
We can have a couple of questions.
Yeah, maybe. Are there anybody would like to ask any question or make comment? Okay, I have a query with this last presentation, Dr. Sharma.
Yeah, sir. Please,
yeah. I'm sure you must have done the work. Do you have any confirmatory things like XPS or anything for your platinum and
sure,
copper?
Sir. Sure, sir. I didn't show that, but it is
sure. I would have expected.
Yeah.
So is it completely you're reducing the total platinum?
Hello,
Dr. Sharma?
Yes, sir. Yes, sir. I can hear you. Yeah. Okay. Actually, we used ethylene glycol, sir.
Yeah, I understand.
Yes, sir.
You started with a platinum 4+ salt or 2+ salt?
It's 4+, sir. We used chloroplatinic acid.
Okay.
And copper is copper acetate. We use it, sir.
Okay, fine. Good. So you have the XPS, no problem.
Yeah, I have, sir. Yeah.
Absolutely fine. Okay, all right. Anybody else has?
Thank you.
Anybody else has a query?
Yeah. So this is Rangarao here.
Yeah, sure.
This is again to Sharma.
Thank you, sir. Thank you. Please, sir.
Sure.
You know why you have not shown XRD, X-ray diffraction of this?
Sir, this is due to the limitation of slides, sir.
Okay. Yeah, but does XRD show any difference in the deflections in the alloy? Is it alloy or individual particles?
It's a kind of alloy, sir. Platinum copper is like an alloy, sir.
So if it is an alloy, you will see nice signatures in in XRD.
Yes, sir. There is a shift in the XRD peak, sir, when compared to pure platinum.
So there is a shift.
Yes, sir. Yes, sir.
Okay, so that needs to be confirmed. Otherwise, you end up having platinum and copper separately.
No, sir. No,
And then
sir.
the entire job will be done by platinum.
No, sir. It's an alloy, sir. It is there, sir, in the paper which we have published in synthetic metals, sir.
Okay, good. Okay.
Thank you, sir. Thank you for your encouragement.
Yeah, is Pooja there? Can I ask a question? Pooja? Pooja Prashantan?
Yes, sir.
Can I ask a query?
Yes, sir.
Yeah, so you are having fibrils formation.
Yes.
What is the kind of evidence that you have?
We have taken images, STEM and SEM images.
Okay. So you haven't shown that, so that's why I was
No.
asking. You have a clear-cut
Yes.
fibrils.
Yes, sir.
Okay. Did you do any THT titration?
Yes, sir.
Thioflavin T?
THT titration we
Yeah.
had done.
You had done. Okay, good. Good.
Yes.
Yeah, at least you should mention. You don't need to
Okay.
show all the things. Okay, good.
Okay.
So anybody has any other query?
Yeah, I think I don't remember this presenter's name.
It's okay, no problem.
I think it's your student.
Who?
The drumstick work.
Yeah, Sirlata. Sirlata, you have a question.
Yes, sir.
Yeah, go ahead. Professor Rangarao, go ahead.
Yeah. See the drumstick powder. How did you make that powder?
Sir, actually, initially we just make the powder by defatting it. First, we'll make normal powder and then we'll defat to remove the lipid content from it. And after removing the lipid content, whatever the remaining drumstick seed powder is present, that we have used for initial studies for normal dye absorption and heavy metal ion absorption.
Because looks like it's working very well. I think you have published also.
Yes.
But what I'm saying is, in the drumstick you have several things. One is the skin, and then you have that hard material, and then inside you have this.
Yes. So initially, the first hard material will be removed from outside, and then the inside material will be powdered, and then defatted with either THT or petroleum ether.
So this drumstick is a what? I mean, is it a well ripe one, or how? I mean, you.
The dry seeds, not from the normal drumstick which we eat. The seeds will be dried, which will be commercially available actually for any studies. So the drumstick seeds will be dried thoroughly, and then the skin will be removed, and inside material will be used for the powder preparation.
I see.
She has basically purchased the seeds.
Yes.
Seeds, not the drumsticks.
Oh, seeds. Okay.
Yeah. Seeds are readily available in market.
Oh, I
she
see.
takes. Yeah. From there, she does the further processing.
Oh, okay.
Yeah.
So that's a good thing. I mean, there's a good application of that.
Thank you, sir.
Yeah.
Sir, I am Sharma, sir. I have one question to Srilata.
Yeah, please.
Yeah, thank you, sir. Thank you for allowing me. Srilata, your presentation is very, very nice and wonderful.
Thank you, sir.
I would like to know whether you tried any kind of your material specificity towards organic pollutant removal other than the heavy metal absorption.
So actually, this work was focused on organic dyes and heavy metal ions.
Okay.
So in dye removal, we showed specificity because the protein has cationic nature. And we were able to show even the degradation because copper was present in the copper phosphate from which we use prepared nanoflares.
Okay.
So from the protein presence, the adsorption takes place, and because of the presence of copper and presence of H2O2, degradation takes place. So this is one kind of organic pollutants. We could probably even explore to more content. We'll try to do that.
Okay. Like emerging contaminants also you can.
Yes.
Yeah, very nice. Thank you.
Thank you.
Okay, I think let us try to close down. And first of all, let me thank all the presenters, Professor Vijay Raghavan, Mr. Yunus Ali, Professor Loka Subramaniam Sharma, Ms. Sanchita De, Dr. Saripalli Sudhakar Reddy, and Ms. Sirlata, and Ms. Raka Ahmad, Dr. Sinu Totadi, Dr. Syed Akil, and Ms. Pooja Prashantan. So thank you very much for making a nice presentation that led to some discussion as well. And also let me thank both the chairpersons of the two sessions. So Dr. Roy and Dr. Biswas, who has conducted this program quite well. And I could say that, so we started with 85 number, and now we are 58. So it's only just reverse of the number, not so bad. So we're quite all right. We are quite all right. And I hope tomorrow we have all these. Those who have presented today, please be present tomorrow as well. And we have many more exciting presentations. As you see, even the flash presentations are very attractive. It's not that we should undergrade that. So we have to really honor all the presentations, even by the students, faculty, everyone. So kindly make use of this opportunity. 9:15, please log in by 9:15. So all those who are there today, please be there. And then I'm sure it will be bigger in number tomorrow, because most of the people who are for tomorrow have not logged in today. So I think we could probably control this. So you will be getting your certificate only if you attend both the sessions. Okay. So that has been announced even earlier as well. So
Sir,
not, yeah, yeah. Please, Rajiv, go ahead.
yeah, yeah. So what happened? Yeah, so it was having some feedback. So yeah, so we have taken attendance couple of times today. So we know who all are not here today.
Oh, okay, okay. So it seems there is some monitoring going on. So be cautious. So you, so that's okay. So good. So I think it's very good, very nice, and we have a good number of people. All that. So I must definitely thank everyone. Several of our faculty colleagues are still there, and so I thank everyone. And please be there by 9:15 tomorrow morning. Any other announcement, Rajiv?
I don't think so. No, sir.
Okay. Okay. Thanks
And
a
yeah,
lot.
abstract book, we will be sharing the link.
Yeah. Thank you, Professor Rangarao, Professor Mangal Sundar, Professor Gautam Lahiri. So really, thanks to you all for sitting through. And yeah, it's
Yeah.
really a nice thing.
Good
So,
job. Good job. Very nice.
thank you, Rangarao. Thank you,
Congrats
Rangarao.
to all chemistry department faculty.
Thank you, thank you, thank you, thank you. They deserve. No, we have one more day. Let us wait for another day, and hopefully we will have similar enthusiasm and the support tomorrow as well. Okay, shall we close down?
Yes.
Sure, sir.
Yeah. Thanks a
Sir,
lot.
I have a small request.
Yeah, please.
The sessions I noticed were all being recorded. And please take the help of Professor P.S. Natarajan and his DTH Swayamprabha team to edit the videos on an individual video link. They will be able to edit the videos one at a time.
Okay.
And provide the title, and the title
great.
slide is already there.
Great.
The slides can be there. Now, basically, the video library can be your first library for the conference run in IIT Tirupati from the chemistry department. And all these videos can be linked later, as well as can be provided as an archival in your system. The students will also love to download their own videos, what they have done. They are very useful. For the plenary, the faculty speakers who spoke for 25 minutes, it'll be really nice to have them put together. And let me see if I can actually broadcast them on a specific day in the national media for a whole day, whatever time. So it should not be. Please, I'm suggesting this. I hope.
Absolutely, absolutely. Thank you very much for a nice suggestion, and you are also a member. You are a main person in the.
That is why I will tell Professor TSN with a request that his team help you with the editing process.
Yeah, we will try
that. There is a standard format for the webinars that we created. Your lecture, sorry, Professor Vijay Mohan's lecture is now ready. I don't know whether I have sent it to him, but I will be sending it to him.
Great.
Tomorrow.
Okay.
So we record them and we keep them.
Yeah. So Rajiv, let's follow that. Once let us finish this program, and then we will go get these things done. Okay. Yeah. Later on. So we can take.
Extremely well
can.
done. Thank you.
Thanks a lot. It's all by everyone spending their time. Yeah.
Yeah, that's why, it's important to have Mangal Sundar on board always.
No, everyone has something or the other to contribute.
He will give this kind of nice ideas,
Yeah, sure.
And he has the infrastructure to do all these things also.
Yeah, right person.
The right person.
Is absolutely right person.
Yeah.
Thanks a lot. So it's a little long sitting for everyone. I think you deserve to be moving a little bit out from your seat